my guest to log on. Welcome, guys. It's Friday night, April 24th. We're going to have some other people, hopefully a physicist joining us, a friend of Skylar's, to come and help throw some his ideas into the mix. We got some news coming up. I want to talk about some of the some of the new stuff being posted. This video was posted by Star Drive Report yesterday, and it was another update from Jack Sarfatti. And Jack pretty much just lays down that this is like the Manhattan Project, that we have the theory for how to create the next step in atomic energy. But what they really need was all the Oak Ridge laboratories and the kind of underground networks to pull together to build the materials to get the refineries that produce the uranium and plutonium that led to the success of the Manhattan Project. And that we basically need something like this going on nowadays, only with the hunt for metamaterials and these new age types of space age materials with these unique properties of affecting the near field to basically create inertial cancellation and other types of super futuristic awesome technologies. And in the midst of that, we get this Wolfram project going on, and I'm still 10 days left on my trial of Wolfram Mathematica. And I'm trying out. I'm already breaking his software and his computer algorithms with some of the stuff I'm coming up with, just based on we've done a lot of thought experiments the past couple videos to kind of come up with an idea for the geometry of the universe. And I also want Sebastian here, my guest, to why don't you talk about that, and you can maybe even share your screen with us. And
yeah. Absolutely. Whenever we're ready to do that, I got a couple of things I want to show you guys today.
Yeah, you've gone a lot more into this. We've done a lot more of the work on Sebastian's computer. Actually, he's more the computer programmer and better at doing a lot of this stuff than I am. But we share ideas and kind of come up with things from just from looking at basics of physics. One of the basic things that I wanted to stress and drive home is the fact that there's black body radiation, that the universe doesn't exist really. It doesn't. It's not like physical unless it's communicating with the rest of the universe, unless it's talking in a constant information exchange. And that's what goes on as things cool down. The information cools off too, and it's interesting how everything is based on this idea of
Everything is hyper-connected, right? Like what I'm seeing my own work playing around with what I've been playing around with is essentially that from what I can see, it seems as though the universe is hyper-entangled. Reality is completely and totally entangled with itself. It just looks like, it looks to us here from here that there are things going on and all this stuff happening. But at the end of the day, it's a single thing that's been biased and recombined with itself over and over again to make it look like as though something actually exists. That's the only way I can describe it based upon what I'm seeing. So it'd be interesting to go through this with you guys.
All right. So let's why don't you share your screen and
Sure. Let's get started.
I've been breaking this program.
All right. Here you go. Can you see my screen?
Yep. Yeah, we can see this now.
Excellent. Okay. So what I have here is a really, really simple algorithm, but it's fascinating. Essentially, what I'm doing is I'm taking nothing and something, and then I'm biasing it with itself. I'm joining it with itself over and over and over again. And from that, from that process emerges something that looks like this, right? So what I'm doing here is essentially creating a set of points. Now let me just run this so you guys can see these numbers come out and get a better idea of what they look like. Yeah, just rerun it like this. I think this will do. And we'll go evaluate all cells. And Jeremy, as you can see, the formula I'm using doesn't use at all the Wolfram model. Uh-oh, why doesn't it like that?
I was still having an issue with my mic, my audio. I just unplugged it and plugged it back in.
Hello, how about now? Oh, there we go. I think my mute button was on. Check, check, check.
Okay.
How's that much better? Is that much better?
That sounds good to me. I hear you great.
I think I got it. Sorry about that.
All right.
I hate when my mic. It's always an issue. So. It doesn't. It's not like it tells me. You know, I have to wait till I'm going. I checked the audio and it said it was working, but it wasn't at the right level. But anyways, you can hear me now. We want to talk about. I want to talk about some of the basics that led us to this idea and this theory, and it goes back to this kind of idea I had, 10 or 20 years ago. It seems I can't remember when I first had it, but this idea, I think it was the first time I went in one of those elevators that had the mirrors in it, where you just have this mirror on either side that reflects the space in between into infinity. And I just had this vision of like, oh, what if the universe is just this fractal of nothingness that's reflected into infinity forever, because all the we have these theories of relativity that tell us that everything's just relative, that nothing really moves, it just moves in relation to something else, and that energy is like conserved, and that all these reactions that happen, there's an equal and opposite reaction, and equal and opposite sum to zero. So there's always this nothingness that's preserved in all these reactions, it seems, that are universal and possibly just reflections within this symmetry, this lattice of a hypersymmetry of some kind.
And and everything that you're saying right now is exactly what I get out of looking at this simple equation that I'm looking at right now, because it's a good illustration of that. So if you look at the top, for example, we've got a single node that's doubly connected with itself. So really, you can't, on its own, mathematically, you really can't say much of anything about this node. It could be nothing. It could be everything. It could be infinity. But let's call it infinity for now, because that's what it looks like, and we might as well put a name to whatever it is, right? We can't, because you can't really tell. But then the next and the vector for that, the points for that are basically 0, 0, 0, 0. So it's a completely still system. Nothing's going on, no change, no difference between elements in the system, right? Completely blank. Then we move on to the next element of the system, which is essentially a perturbation in the symmetry of that nothing, where essentially half the symmetry is perturbed by creating a new point in space. So now we've got a 0, 1, 1, 0 here. And what that does is it describes 2 points all of a sudden, right? We still have the flow happening between the points, so we can call that flow whatever we want. Movement, flow. I've been calling it flow for lack of a better name, but essentially these points as related to each other.
I call it entanglement.
What?
Entanglement.
Right, exactly. These are fundamentally entangled they're not even particles yet. They're just points. And I look at this as kind of like polar opposites. Here we have.
Here's the idea is that space and time are really the same, and that there's no mix up, and that
right,
everything's just space, including matter and energy is really just is different representations of space, and that this is entangled space. So I call them entanglements, and these are just nodes that are in space, points that exist in space.
Exactly, points that make up space. I even look at them as, right? And so in this state of this particular system here, we have these two points, but two nodes, but they're unbalanced because they're here. That's all of 2 nodes, each of which has a connection to the other. And you could say.
And so why is it doubly connected in this first one? Is it just to make it look like infinity?
In here? because I'm using a doubly connected. I want a doubly connected nothing that I could bias half of, essentially, is what I'm doing. Right?
Yeah, because that's sort of the way to model this whole idea I had. Because I was like trying to like, how could we mathematically model this of the idea of nothing looking at itself, and
Yeah.
it's and this kind of incorporates consciousness into it. I feel because it's like nothing that's acknowledging its own existence and looking back and reflecting on itself. You know what I mean?
Absolutely, absolutely. I mean, if you look at do you see how those arrows are even pointing to each other? I didn't do that on purpose. It just kind of came out of this particular graph.
Yeah,
So
it's
okay,
cool. It's cool that it looks like infinity though.
right?
But
So the next generation of the system, there's something really important to keep in mind here. All activity revolves around the zero in this particular algorithm, meaning that there is actually nothing happening in the center of this algorithm, and zero is not really symmetry. So you've got this bilateral symmetry here all of a sudden now with a still point in the center. So and you've and by doing so, now all of a sudden you have a point in the center that has the same qualities as this one, but is actually something real because there's perspective, right? So it's important to keep in mind, like, all of the basic things that we think about, like perspective, point of view, self, other, one, zero. These things are fundamental concepts and principles that must go into, I think, any, like, finding anything that has any kind of meaning to it. Anyways, as the system evolves, the interesting thing about it is that it's actually spinning on its own central axis here, right? So in each place, the 0 point is always at the center. And actually, interestingly enough, if you try any other combinations of interconnections here, this doesn't work. So that what that says is that every point's flow goes through the 0 point and out on every point is connected back to that original point. So it actually goes, it makes sense, right? Because everything is entangled back to the thing that
right.
it was created from.
Right, that everywhere is the center of the universe too.
Exactly.
Every point in the space, the laws of physics should be the same.
Exactly. And from there, the way that this graph here grows is pretty straightforward and simple. It just grows linearly like this as the set increases. But what I'm about to do now is do something that I saw that was really interesting in another set that I was in another drawing that I was playing with, and that is essentially iteratively combining itself with its last generation. So, or doing an iterative replacement of the last generation into the current. So, for example, taking the 5 here, right? These are 5 points. Taking the 5 and replacing the 6 with elements of the 5 to see what happens, right? And I think that, and if you do that from the start, you actually immediately start to generate a phi, and it's obvious why, because you're taking the whole of the last iteration, you're combining it with yourself, and so you have a natural progression that's happening right there in space. But whether you are rotating this, whether you're adding a point and then rotating this this diagram, or you take the one before and combine it with the one now, the result is always the same. So you can actually generate this set in several different ways that are all kind of that are all essentially you're aggregating to your last to the last iteration. So there's this concept of essentially natural growth, and it's interesting to watch this emerge and to kind of see what comes out of this. And I'm really enjoying playing around with this set, and I've got some ideas about how I'm going to turn this into an act. Once I can figure out a way to very simply create a large space of interconnected points with this, then I'm turning this into a cellular automata, because I think we will find interesting behavior if we essentially set up simple rules to bias these particular connections, right? So each of these connections between these points is actually represents 4 bits of information, because you could have them both be in a particular kind of state, for example. So let's say red, blue, right? So if they were both red, red, that's a highly biased state. Red blue is, you know, +1. Blue red is -1. Blue blue is -2. So you have these 4 states that you can bias here. My idea is basically to as you bias, or as you like influence a piece of the net, what will happen is that force that you're affecting here will be transmitted through all of these points and out into like the edges of the grid, essentially in a way that isn't so much. Well, I don't want to talk about it right now because I'm still trying to figure out exactly how to best describe it even, but essentially the idea is to have a grid that's always essentially vibrating, and when a part of the grid is affected, it naturally will transmit that information immediately to every part of the grid. So that's kind of the ideas that I'm playing with right now. And so far, sticking to basics is like really has been the most interesting. Like, it's fun to play around. I've played around with building all kinds of cool structures, but the really fun stuff is in the basics. Like, you know, dividing something by itself over and over again, or adding 1 to something and then adding it to itself. Those simple things are like, you know.
Yeah, those are the ones that get the chaos, that seem to produce the most amount of chaos, because it's fluctuations around this point that never seems to get back to where it started, or it never seems to get anywhere.
Yeah.
It doesn't blow up, it doesn't diverge, it doesn't converge, you know?
Yeah. Yeah. So this is just, you know, this is kind of the beginning of this a little bit playing around, but mathematics is pretty powerful. Like, I figured out ways to ditch his method altogether and just use simple math to do it, which is the way it should be. Like, I should come out with an algorithm that looks fairly simplistic but produces a lot of complexity if it's, you know, if it's anywhere what it's supposed to be. So.
Yeah, so we just keep. We've been trying different things, different starting conditions and different rules, to try to generate different things. Some of the concepts also that I wanted to point out, that I thought just from some of the research I've been doing into Polyhedra. We started with, of course, the Platonic solids. That's a very you know, this should be, I feel like this should be taught, and I don't know why it wasn't taught to me at a younger age, but this should be taught to elementary school students. This is really key stuff here. What I thought was interesting is that the tetrahedron is the most basic, and it's the self-dual. It doesn't tile the plane completely. If you can't tile the plane fully with tetrahedrons, you'll always have like these gaps in here in the spaces. You can tile the plane with a combination of octahedrons and tetrahedrons. That will tile the plane, but not tetrahedrons alone. Tetrahedrons are also really interesting. I think they're the closest to resembling that electron, if we were to think of that electron structure. But the next step, also that the self dual in with itself, kind of like, it looks like the first electron orbital, that S2, or you know, the S orbital with two valence spots, you know. I think it kind of, I don't know, I'm trying to come up with a scheme for, we're trying to come up with a scheme for generating the periodic table of elements, and figuring out how to get matter, you know, the structure of matter that comes out in the periodic table of elements, and also not just the periodic table of elements, but also that explain the fine structure constant and some, you know, some of the more finer details of the quantum nature of these particles. But I think it has a lot to do with polyhedral combinatorics, and just combinatorics in general, because these polyhedra, the shapes at this structure of space, this is where at this structure of space, this is where all the hypergeometries and hyperdimensions seem to be able to exist, and this is what physicists are finding with their experiments, and some of the theories that, you know, they've been going through with string theories. They're like, oh, these hyperdimensions exist, but they're only in this wound up little space, and they don't really go anywhere. And like, how we're trying to figure out how this all works. And I believe this is the path, you know, just understanding basic functions like this is the path, you know, to figuring out how to create things that function on because they're not just polyhedra. These are very simple. These are very simple shapes. They're actually shapes in space which are much more higher dimensional, like that. That E8, and some of those
Right.
other structures that are really hyperdimensional. I covered this some in the last video. What was the thing called? It was P. I forget what it was called.
Mm.
But we had these shapes. I'll find it later on when while you're talking, and
Yeah.
bring it up again. But that's the whole idea that brought me to. Is this was the idea the ancients sort of had. It's interesting when you go back to some of the Greek mythology. These ideas, they thought that, for example, the octahedron was wind, the tetrahedron was fire, the cube was earth, because it was
Yeah.
kind of like Minecraft.
Totally. It is
and,
like Minecraft. I
and
think, but you never know. I mean, reality is probably exactly like Minecraft in some ways. Like,
right,
you
and
know, if
that
you,
water was the icosahedron. But we know now that actually through polyhedral combinatorics, that it is these types of, again, this is very much like our connected graph structure that shows, this is just a tetrahedron.
right.
I'm not sure if is that really that complex to show this tetrahedron. Oh, this is how to find the angles, or what is
Shouldn't
this?
be. Showing a tetrahedron is fairly straightforward.
Yeah, this seems like a more hyper-connected geometry. Who are watching this, trying to come up with conceptualizations to sort of understand this and
Right.
visualize it and relate it to something physical. That way, we can start building the physical universe from these hypergraphs in a manner that works towards our model
So
of
I've got some
physics.
philosophical, well, maybe not philosophical questions, but they might be. So, so if things work the way that we've been talking about here, essentially, you could say that if you knew, like, you could theoretically say that everything is deterministic in some way. But I was thinking about that last night, and I'm not so sure that could ever be the case, right? Because first of all, causality moves at the speed of light.
Yeah.
And so that's pretty slow compared to a system that's likely to have information move a lot faster than that. If it works the way that we've kind of been moving towards, that means that essentially whatever the substructure is, that is the interconnections between all of these, nodes of reality.
Yeah.
That information got to travel at, I don't know whether there's
It's the
even a
speed
speed
of
on
quantum entanglement, and then we haven't measured that yet in the laboratory. But once we measure the speed of entanglement, this will help us actually design experiments to measure
right.
that.
To me, the speed of light is caused probably by some type of like interference front between two scales, where you probably at some scale you have like some behavior, something that manifests itself as light, basically a ray of something that moves in a particular direction at maximum speed through its kind of matrix that it can, right? But it's still limited by something, because there's the matrix itself still is connected, hyper connected in a certain way. So it doesn't, I don't know what the hell I'm talking about, but I feel like there's something there relative to kind of the differences between kind of what's at the root of reality and the kind of the emergent properties, the emergent phenomena that happens on all this. Because if you have a bunch of points that are all connected with information that can move between them, if you perturb any location, that information has lots of options for how to move, and depending on the rules, could set itself up to start moving in stable vortices. That's like eminently possible that I'll see that pretty quickly in doing this. I've seen similar stuff with cellular automata. So,
well, the interesting thing, right, is according to the law of black body radiation, that if we have a piece of material, it needs to be at a certain temperature, and then it's slowly, what's going to happen to it is if we just have it in this model all by itself within a universe with nothing in it, what it should do is slowly radiate all its energy away until it cools to absolute zero, and starts like
yeah.
basically disintegrating.
Exactly. And so my what I picture in my head is this hyperconnected grid of these points that we're looking at, doubly connected. And at any particular moment, the perfect grid would look like half the points are biased in one way, half in another. So you have this essentially like vibration that's fast and balanced, and you can't tell that vibration is there because you're part of it. But then something perturbs that grid, and all of a sudden, in a particular section, more of those connections are biased in one way or another because maybe the information's trying to get out of each other's way as it flows, and something happens to like slow that information down. And from those biases, from those kind of from that turbulence comes these kind of emergent effects. That's my intuition.
So
That's what I'm looking for. As soon as I can make this, what you're seeing here, turn itself into a interconnected grid, and that's the hard part, because like I think about it in terms of what you were saying, where you have a mirror. Let's say you're in the middle of a cube, right? Of a cube with mirrored walls on it, and so how do you? I guess I have to just look at the algorithm for how a ray of light extends from a center point, and then essentially duplicate my structure as those rays of light go out. I guess, I don't know. This is stuff that I need to learn here. I'm missing some of this mathematics because I don't do this every day.
right.
Computer, yeah.
I just want to answer a couple questions. Minecraft, procedurally generated. Yeah, well, the interesting thing about cubes is this: the only Platonic solid that tiles the 3D plane. You know, that tiles 3D space is the cube.
That's right. Nothing else will fit, right? So I think that's a big hint.
Could be a hint to which one, what produces our, dimensionality. What is it, three edges on a corner that's mirrored, or,
Yeah.
How do
But
we
what
do
it is exactly is I don't know. I feel like maybe it's like a hyper connection of like even the reflections in the center of the cube, though even those that reflected stuff becomes actual stuff in this model of the universe, right? So you're looking at, and you may see like grids transposed onto each other. I don't know. I have to look for I think I just have to look for a rendering of what it looks like in the center of a cube.
All right, so I'm gonna draw a cube out, and then I'm gonna because someone asked me to render this and see what a cube looks like. A, B, C. All right, so I'm just gonna go 0, 1, 2, 3, 4, 5, 6, 7. That's our 8 points. So 0 is connected to 1. 0 is also connected to 2. And 0 is also connected to 4. Oh, this will be fun. Right, so let's make it symmetric. No, you know what? Let's try it not symmetric first.
Are you using nodes to render this?
Yeah, I'm gonna use nodes to render a cube. So what I did, is I took. I'll show over here what I did. I did 1, 2, 3, 4. 4. 5,
Yeah.
6, 7, 8, where that would make a cube,
Yeah.
Right, so this is going to make our cube.
Huh?
we'll draw these points, and then we'll label, you know, and then you label them all out, and then you ask, all right, well, see, this is 0, if this is 0 and this is 1, you know, oop, that's a little big.
I think, I don't know. Just looking at this stuff makes me want to say crazy shit. Like the circle and the square are equivalent because they're both 360 degrees. Why do I say that? Well, first of all, I mean, they do, their corners add up to 360, but when I look at the graphs I generate, when I see something extending out in like 8 nodes that way, I immediately think of it describing dimensionality, and I think that's because that's what it's doing. Like it's almost like as like when the universe is being built, it's like this thing is revolving in space really, really fast, and then projecting out in that way, like it projections into it. Because if you look at the math itself, that's what's happening to the model. So
Yeah.
oh my God, I wish I could make sense.
Yeah, not crazy. No, there's no crazy thoughts here, man. This is the brainstorming session, and you know.
Right. Yeah. I know what I mean, but I just don't know how to say it.
So I'm going to explain this to people, what I'm doing. So I'm going to have the arrows going this way, so 0 connects to 1. Why don't we have everything go from 0 to 7, right? So everything comes from 0. So 0 is the first number because it points away from 0 in all these cases.
Mm-hmm.
So it's going to go from 0 to 7. So then 4 is going to be connected to 6 and to 5. So, comma, 4, comma, 5, comma, 4, comma, 6, comma, let's see what's next, right? So then 5, all right, so 1, we're going to have 1 go to 1 connected to 5. And then 5 is connected to 7, right? So 1, comma, 5, comma, 5, comma, 7. All right. And then 2, comma, 3, and 2, comma, 6. This one's gonna be funky.
Uh-huh.
I can't wait. This is fun. All right, so then 6, comma, 7, 3, comma, 7.
Oh, that's interesting.
All right. All right. So let's just try it with our simple rule of just doing one side. All right. What's gonna be here? Oh, so I gotta close it on the end. Yeah, it's always something in this. You'll find. Oh yeah. So there's our cube.
Nice.
Oh wait, so it's not figuring this out. It's doing weird stuff. I might have to clear the plots, right? So delete all outputs so it doesn't get them confused.
Delete all output is usually the thing that'll fix your problems.
All right.
Yep.
No, it's still going back. I gotta wait for it to finish what it's doing and then do it again.
Oh, there is also in that same menu, there's something that says stop current evaluation, I think is what it says.
So there's
does what it means.
Find 0, 0, and what I want to do, I want to change this so that all right. Oh, sorry. I freaking did shift enter.
I'm gonna relocate so that I can see your screen better because and that way I can help you get through this too.
All right, so we're gonna do search equals, right? And I want to find, because we don't have 0, we don't have these shapes anymore. So we're gonna search for all the points should go to 7. So let's search for 5, 7, 6, 6, 7, 3, 7. Right.
So as I don't know, as I'm playing around with this, I'm starting to like see concepts that I think I'm sure are a thing in math, but I can't, I don't know their names. Like, for example, if I'm throwing out like rays of nodes as I'm rotating, what I noticed is that really like each number has a particular kind of like describes a particular angle on a circle, right? So like the number 2 bisects a circle in 2, so that's 180, and then the number 3 is a 120, and then 4 is blah blah blah, right? So the bigger the number, the angles correspond to have a correspondence to that number that's meaningful, because no matter what the number is, it's just, if you think about it going around in a circle, it still ends up in a particular place. Like it never, what the hell am I guess this must be like geometry and sine and cosine and tangent, probably, is what I'm thinking about. So it's an interesting way of thinking about a number as well. Like, there's other ways of thinking about numbers that aren't kind of the way that we're used to, in terms of just adding these things up. Numbers can be things as well. I think they're like, I don't know, all kinds of crazy ideas trying to make their way
Right.
to my.
Well, numbers. Numbers are abstract meaning. Numbers aren't really things. They just represent, how many things. It's
Right.
abstract value that we apply to things in general. And what combinatorics teaches us is that there's different ways of counting things.
Right. That's what. That's what I mean.
So combinatorics is very interesting, and I encourage people to take a class on it if they can. And I want to go more deeper into it, because I only took one semester of combinatorics. I want to go a little bit deeper and learn polyhedral combinatorics, which is like the real how to make all the different shapes, including hyperdimensional shapes and all that fun stuff.
Okay.
So this is really some key math for understanding everything. But I don't know, a couple of things in that I learned in combinatorics was a couple things, ways on how to count things, like shortest path, right? So
Yeah.
shortest path, how to calculate shortest path, and there's an algorithm for it, right?
Yep.
And it's a computational problem, shortest path problem.
Yep. Traveling
And
tail, pretty common in computer science.
right. So this is it. If you want to read up on that, that's I'm not going to go into it. It's more of just an introduction. This is an introduction video, so people have some of these concepts that they can go and fill in. So you get all the basic skeleton, and you can go fill it in with the meat and the
Nice.
nerves, and here's the bones, though. Right.
Nice.
Shortest path problem is one of the things. So another way of counting is the choose function.
Mm-hmm.
So how to use the choose function. This is how to do it in Excel. But I want to in math, combination it's called, right? This is a key of combinatorics, is combination. I didn't share these originally, so I'll share these in the live chat and a live stream, so people have those to link to. Combination, this is the choose function, and this is read, if you ever see n over k in parentheses like this is read as n choose k.
Got it. And what does that do? What does that algorithm do?
This is basically, so if I have a group of n objects, how many different ways can I choose 4 out of that?
I see.
So it's kind of like partitioning sets, partitions. Partition theory is a key part of set partitions of a set.
Is there anybody out there playing with this stuff currently, by the way? Anybody watching this video that's been playing around with Mathematica or played around with this?
I don't know if there might be some people that are more advanced on this number theory stuff and who understand it on a deeper level, but this is stuff that I've learned about and I've studied a little bit. I know about it, but I wouldn't call myself like an expert. I wouldn't, I'm not like a college professor on it. I wouldn't be able to teach a real good course on every, and understand it like super well. Oh, Catalan numbers. That's another interesting thing of set theory that has come out.
Have you ever considered what might have happened during the period of inflation, as kind of described in our current theories of the Big Bang? If that in fact did, do you have any kind of method of effect that might have, like, what might have happened there? Like, how all of a sudden did it? Like, what do you know how fast it blew up to the size that it did? Was it like a matter of?
There's calculations for it and stuff, but they're based on our present day models, and this is like a new model for everything. So we don't know, like, for example, the models that we have, they're tweaked one way or the other based on something called the cosmological constant that Einstein kind of put into the model, and has been there. So the cosmological constant, right? And this was something that was Hubble in his telescope. He saw that all the far galaxies are redshifted, so they're moving further and further away from us, and they're actually accelerating further away from us at the ends of the galaxy. So, that supported this idea of this, this. So there's three different cosmological constant equals 1 is like a stable universe that's constantly inflating and deflating and like this rhythmic, universe. And that's kind of like what I would hope and expect, and that's what you kind of get from this model, assuming that supersymmetry it holds, that CPT and supersymmetry hold, right? But if supersymmetry and CPT symmetry aren't holding, and it's a little bit off-skewed universe, then we should expect one of these other sides where it either expands infinitely into nothing, which is called the big freeze, where everything just spreads out and cools off, and then or gets sucked into black holes and all the information just disappears into a vacuum cleaner. And the other theory is that that it spits out the information at the edges of the universe. It's always more, something's being created more, so that theoretically you could escape this big this destruction of the sucking of the black holes if you just keep moving further away from the black holes at the towards a different edge of the universe. But then where's the edge of the universe, and is it the black hole? Is the black hole the edge of the universe?
Right. I mean, it's certainly the edge of the universe is certainly not our observable edge of the universe.
And what's the shape of our universe?
What's that?
And then what's the shape of our universe? Are we living on a torus? Then how do we know? Like, how can we really tell or know? This is like flat universe theory, but
yeah. Exactly.
I call it flat universe theory. It's like flat Earth, but
Oh my God. Anything but that.
No, I'm sorry I brought it up. But anyways,
oh my God.
back to
drives me to an instant rage. Like, if I want to feel angry, I just go.
Yeah, just go Google that for a minute, and until I saw. I just go watch. I get that way too. Then I go watch the guy who in the rocket ship launch himself into space.
Oh yeah, the guy. Did that guy die?
Oh wait, he died. Yeah, that's right. That's not funny. You can't joke about that
poor
anymore.
Guy, like, poor fucker. Like, no, it is funny, bro.
He won a Darwin Award, right?
That is funny. Like, I mean, I salute him.
Like he won a Darwin Award. Like all the people like protesting and going out in the virus and stuff. It's like, come on, you guys. You don't think that's like engineered? And, it's like the people that go get these tests and the vaccine, and then they end up getting coronavirus from it. And then,
You're gonna line up and get the Gates vaccine.
the Gates vaccine, right? Oh yeah, they got a place right down the street from me. I was joking, like we should everyone should go and like make signs that said depopulation center right here, and like
Like my policy right now is not to touch any of these topics with a 10-foot pole because it
just
makes
not
us all crazy.
no, it just
most sane people on my feed like crazy as fuck.
Oh, dude, the coronavirus conspiracy, it just goes nuts. But anyways, this is much more fun. It gives me a break from all that madness, because I was getting sucked into that 5G stuff and doing videos on it, and digging up all the CIA's manuals, the Russian, the Russian KGB manuals on all the bad frequencies, and and I got pretty sure my videos, I got some shadow ban on my channel for covering that kind of stuff and talking about that shit. So
I'm sure it's like it's well, it's such a. I'll tell you what. If I was the cell phone companies, and I wanted to make sure that nobody would ever fuck with me about 5G, I would immediately put out a ton of this kind of disinformation that we've been seeing about 5G now. Make people crazy as fuck, so that if a legitimate conversation ever came up about 5G, that we could shut it down fast.
Right.
So that's my conspiracy theory. I don't believe in the 5G fucking bat virus, but I do believe that people will protect their financial interests.
Yeah, the virus is real, and you got to protect yourself from it. And if you're going out and protesting the lockdowns, that's cool. And I'll put more power to the people for doing that. But just be safe, and be careful, because there are these shady groups of COINTELPRO and other things that want to collect information on you and want to use biological weapons against you. So there's someone in the crowd that pretends to be on the side, but meanwhile he's spraying coronavirus on your back.
That's what I like. That's that's why I don't go to protests in general.
It just friggin' scares me. What?
All right. So.
But if you already had the coronavirus and you're immune, then that's fine. But I don't know what the heck's going on with that, and I don't want to get into it. I'm sorry I brought that up, and we're not going to go down the flat Earth rabbit hole. But okay, so more things from Combinatorics. Combination is a key thing of it, and it can be written using this Factorials function. Factorials are a very interesting. Anyone who's had a scientific calculator and you see the exclamation point on it, and you're like, oh, what's that for? Well, it's the factorial function, and that has a that's what's divided out by these factorials, because that's all the numbers in the set multiplied by each other. So if you want to find out all the different combinations of numbers in a set, it's
factorials. Yeah, now it's interesting that you mentioned that, because I did a version of all of this research like years ago, and I created a program that would visualize frequencies using factorials, and it would take a frequency and it would break it down into its component factorials, and then display a series of polygons based on that. Because I wanted to, I was playing around with some concepts that I got from a video that I saw a long time ago called sonic geometry, which basically talked about some of the concepts I talked about earlier, where essentially you can count within a circle, and that counting generates a set of angles that are actually numbers that can correspond to frequency. So all the Platonic solids correspond to a perfect fifth chords, right? So if you play the Platonic solids as music, it's beautiful music because it's a perfect fifth. And so they're like, and so based on that, I could see that there's certain geometric shapes fit together in different ways based upon their kind of the ratios of their relationships. And so what could I find out about that a little bit? And there's a lot of interesting stuff that tumbles out of that, especially with numbers that have 2 and 3 as their factorials, because they can be recombined in so many different ways that fit on essentially a system that's a 3-dimensional system, right? Mm-hmm. Like things that are factors of 2 and 3 work in our dimension, but they they are like other numbers aren't so good at that, right? And I'm just trying to figure out the hell a prime is about. Like, what the fuck is up with a prime? What is? Like,
yeah, so prime numbers, very interesting. That was one of Ramanujan's fascinations, was always with prime numbers. And
yeah.
yeah, the various theories for how that, you know, and it definitely has to do with combinatorics and how things combine to create other things, and there
I
are
had this
gaps in
idea
this.
earlier about that, where a number that isn't prime, if you kind of like say you draw a number of points out, you know, on the radius of a circle that's equivalent to like your number that you want to be looking at or testing. If you take those dots and you bisect the circle and you mirror it on top of the other side, all of the non-primes like connect with each other perfectly on the other side if they're rotated okay, so this is if they're rotated in to the spot where their numeric
Yeah, it's the Ulam spiral, right? I think this
is that what it is?
Yeah, so the Ulam spiral is this graphical depiction of the set of prime numbers, and it was divided by this mathematician in 1963. This is Ulam. This is the guy that basically inspired John Conway in his Game of Life.
Okay.
Yeah, so this is another very interesting connection. Speaking of connections and groups,
Yeah,
that's awesome. Yeah, it's awesome that you brought that up. The prime number spiral.
and because like we've been looking for a way to test primes very, very fast for a long time, right? I mean, that's what the sieve of Aristophanes, which is sieve of Aristophanes, it's all about. And in cryptography, there's a lot. The primes are kind of of prime importance, no pun intended, because we use them, you know, in our cryptography to do like asymmetric key encryption, all this kind of cool stuff. And testing primes quickly is something that is a big deal. And so would be something like predicting the next prime. I don't know about predicting the next prime, but I feel like there's a way to project a prime somehow on a circle, like reduce it and project it in such a way that you could potentially tell from its kind of its own reflections whether it's a prime or not. Because if something is a prime, when you kind of mirror it onto itself, it should not, its elements should not line up on itself because it's not divisible by itself. So you shouldn't be able to fold it onto itself. Do you know what I mean? Like, does that make any sense at all?
Right, yeah, because it's not a fold. It's not being able to fold. There's no folds, and you know, yeah, I guess all right. Should have some questions calling in, and some other people. Hey, how's it going, Sky?
Hey, how's it going? Thanks for the time.
Hey, so you got a physicist friend that we're gonna add to this conversation here. So let me just find him in a second. Yeah. And Dr. Weird will be added to the call.
Yeah, it's gonna take him like 5 to 10 minutes. He was ready about 30 minutes ago, but I failed to forward him the information because I had to take an emergency phone call, so I do apologize.
Okay. That's all right. Hey, man, we were plenty to talk about and cover. Were you guys watching the last bit on we just talked about the Ulam spiral and Stanislaw Ulam, who influenced John Conway, who influenced in turn Stephen Wolfram to come up with this whole new hypergraph theory, which we're playing around with and trying to, you know, navigate the hypergraph space. So, you get your mic working, and then you can join us. I think he's in the call right now.
Hello, gentlemen.
Hey, how's it going?
Hey, I didn't want to interrupt you speaking, so I waited. How you guys doing?
Good. How are you?
Doing well.
So,
Doing well. Got my chocolate coffee. I've had some pizza, and I have a pack of cigarettes. So. Although I left my sunglasses in the car, so I don't have those on.
So we're talking about generating code for the universe as a fractal, and sort of these new theories in physics that are coming about. And
Generating code for the universe.
yeah, what do you think
Is
about that
this?
idea?
um. Well, I'm kind of on Feynman's side on this one. I mean, at the end of the day, I understand the thing about mathematical physics, which is what we're talking about
Yeah,
when we're talking about this, is that it doesn't have any basis in experiment, not really, and not the stuff that relates to this topic, or even most of the standard model, M to CDM, doesn't have much in the way of experimental evidence to prove it. Nothing that can be independently confirmed. So, I mean, it's the issue is it becomes very easy to say, oh, we know this thing, and then this thing that we think we know builds on and builds on and builds on, and we get to a point where we're kind of in the area of epicycles, and that's a reference to the original, to the Ptolemaic
yeah,
model of the solar system. Meaning that the more they learned about the orbits of the planets, the more they realized they weren't perfect circles, but they have to be perfect circles because that's the way motion always works. So therefore, we'll just add another circle. And that fixed the problem for a while until the precision of the measurements got better, and then they just kept adding more and more little circles. Until Kepler came along and said, hey, did you ever think about an ellipse? And which solves all the problems. But
right.
it destroys the idea. It completely upends the original idea, and you have to
Of the centric
let go.
universe. So the idea
Yeah.
with the Feynman, so Feynman won the Nobel Prize in Physics in I think it was 1963 for quantum electrodynamics.
Quantum
And
electrodynamics, yeah, correct.
and he kind of came up with the path integral formalism and Feynman diagrams to sort of explain how particle interactions work, you know. And so one of the interesting things that I noticed about particle interactions is that they always occur, all the Feynman diagrams can always be, looked at as kind of like a vertex map with energy flowing into a vertex and then energy flowing out of a vertex in two directions, equal, a lot of times equal and opposite.
Yeah.
But forward and backward in time. And also these arrows represent like forward and backward in time. So this is one of the reasons I like the approach that Wolfram is taking. If you go over, he's got the on the wolframphysicsproject.org. You can go on here and find materials and technical documentation on a lot of this stuff. I'm still he keeps updating and changing it, so it gets hard for me to find where all this stuff is. But he has a whole thing on here about explaining, kind of how the path integral approach works through these hypergraphs. That basically all of these particle physics could somehow be reduced to these sort of hypergraph functions of the transition of elements through time.
Sure.
Well, the problem with graphing is that, you can mathematically work, whatever out on chalkboard. I forget what mathematician was it that proved that if you could prove that something is right, then by necessity you can also prove that it's wrong using mathematics. But
this is more pure math. This is like pure math. This is like reducing math to its most purest form of computation. Right. And trying to, he's trying to unify physics and mathematics as a single subject, so that physics will eventually become known as a subset of mathematics, because this is the most purest form of mathematics that should,
Yeah. Well, I have a fundamental problem with that approach.
All right.
Like I said, I'm with Feynman, and Feynman said, no matter how elegant your mathematics, if the experiment says you're wrong, then you're wrong. And what he meant by that was, that he understood that what he was doing was modeling. And the Feynman diagram, when he was asked to describe what it means, he's like, it doesn't it doesn't mean anything. It's just a method to discover values. It's a method that happens to work to discover these values. So, I mean, he put it more elegantly than that, but that's basically what he said. And this is where I get nervous, because I've seen so many examples of mathematics ignoring experiment, like basically, essentially the mathematical equivalent of a back rationalization, if that makes sense. So something happens and you rationalize it as something that it really isn't, but it fits within your worldview. The rationalization fits within your worldview.
Okay.
And I've seen this happen so much with math in terms of, I mean, Hawking was famous for this. I mean, he even said near the end of his life, he wasn't so sure about black holes or about dark matter at all.
Well, I mean, I'm of the opinion that black holes and dark matter and dark energies just flat out don't exist. And, you know,
Right.
we have a very anthropocentric mentality with a lot of dogmatic assumptions that, you know, permeate the modern realm of academia. One of the assumptions being that the universe is bounded by unchanging, you know, laws that are, you know, set in stone and are, you know, primordial and permeate the entire cosmos and never change at all. And we don't know that. You know, for all we know, the universe could have habits.
We assume that's true because that's within even within the precision of our ability to calculate, it doesn't appear to be true. But that's something that is that's one of the original inconvenient truths, where some of the constants that we assume are constants actually seem to vary over time.
Yeah, including the speed of light, the proton radius puzzle is quite a number of them.
Including Big G.
And even that
Big
fine
G.
structure constant is not exactly 1 over 137. It's like, you know, it's a little bit off.
The fine structure constant is, I mean, Dyson hung his hat on the fine structure of carbon in terms of evaluating spectral lines from distant stars, but I think later in life he regretted it that he did that, because the fine structure of carbon is not at all clear that you can extrapolate from spectral emissions the actual structure of it. In other words, you can't necessarily get a homologue from lab experiments on the fine structure of carbon doing spectroscopy with burning carbon and the spectral lines from a star. It doesn't necessarily mean the same thing. Like, you could get the same spectral lines. You're assuming that it's carbon that you're seeing, because that's what it looks like when you burn carbon on Earth. But you don't know that, because you have no idea what happened to that light in between the star and you, and you have no idea how the spectral emission radiation is being affected by the universe as a whole, not only in transit from the star to you, but also just within the atmosphere of the star itself. We've barely cracked. I mean, when people talk about, I'm not trying not to lecture. I'll sum this up. When people talk about what they know about distant stars, I always come back to the fact that they don't know that much about the sun, and we've actually launched probes around the sun, and they're constantly being stymied by the measurements they take. They even had to fudge the neutrino experiment by, I don't know if you know this, but the neutrino experiment to prove that the sun is a fusion furnace came back with something like around 30 or 28% of the expected neutrino flux. So that's not good. So instead of saying, well, okay, maybe the sun isn't a fusion furnace, what they said was, hey, particle physics guys, could there be some mysterious zoo particle that is, transmogrifying somehow in between the sun and us, that's taking the place of the neutrinos that we're not detecting.
I put my toe into it.
And could it fill in for the missing neutrinos? And the particle physicists came up with some particles, and voila! And then they printed the article. Neutrinos found. You know what I mean? So this is the kind of thing that bothers me about the details of these experiments. The LIGO experiment is another example. There's these two black holes that were rotating into each other and collided, and that's what created this signal. The problem is there's not one, there's two LIGO experiments. And since gravity is supposed to be an instantaneous fact, because it has to do with space-time. It doesn't travel at the speed of light, it travels near instantaneously, right? Well, unfortunately for them, or I should say what they didn't seem to mention, was that the other LIGO experiment also registered the thing with a light speed delay. There was actually enough of a delay. So it wasn't at the same time, it wasn't simultaneous. But instead of taking this as evidence of the fact that this was not a gravitational signal, they assumed it was a gravitational signal and then invented a reason for why there was a delay, even though the delay was clearly a light speed delay. And then they said, look, we discovered gravity waves. Coincidentally, 6 months before they were due to lose funding because they hadn't had a success in 30 years. So, I mean, and I'm not saying everybody's like this, but the problem is
there's a lot of experiments that have to be. We're in a very weird time in physics because there's a lot of experiments that we're taking as true, which are wrong. It's kind of like the Piltdown man, was accepted by a lot of the evolution theorists of the time because it fit the models that they had. They were all missing this missing link. Where's the missing link? And when someone produced it, they were all so ready to accept it that everyone took it for granted, and no one realized it was a fraud until I think 100 years later. So
I mean, the same is true you can look at the Great Pyramid of Giza, which is located next to the Sphinx, and the assumption that that it was a Khufu? It's Khafra, yeah. Supposedly it was built by Khafra, and supposedly that was the same pharaoh that built the Sphinx. Here's why they say that. A guy in, I believe it was in the late 20s or early 30s, forget his name, I apologize, you can look this up though, who was an archaeologist examining the Great Pyramid of Giza. He had yet to have a discovery. And the Great Pyramid of Giza was, of course, notorious for not having any inscriptions of any kind. So one day, suddenly he discovers a painted mark in between two stones, in a wide gap between two stones, that resembles a cartouche that refers to Khafra. Conveniently, Khafra was the I believe it was either Khafra or Khufu. We can look that up. I apologize. But that particular pharaoh was the one people thought had built the Great Pyramid. And oh, look, here's the sigil. And so all of a sudden now the Great Pyramid of Giza was built by Khafra. And and it was built in 20 years, which is impossible, but that's what they say.
Yeah, no, there's no way.
And no way. And the Sphinx was also built by Khafra because, well, it was situated, in a particular alignment with the Great Pyramid. And therefore it was built by Khafra as well. So the Great Pyramid and the Sphinx have been dated to the time of Khafra based on a painted sigil by an archaeologist who was desperate for a discovery and just happened to find one.
Yeah.
It's been suppressed, but some German archaeology students illegally were only available in the 19th century and after.
Yeah, it was a lead-based paint, and of course the Egyptians did not have lead smelting technology, so
Oh yeah.
Uh-oh.
Uh-oh.
It they didn't. They
Um,
certainly didn't use lead in their paint. Is the point?
what was this
Um,
that I wanted to look up? We were just on Luxor. Oh yeah,
so
someone pointed out
that's just an
also,
example.
yeah, that you're correct. King Tut was found in Luxor, um,
Hmm.
which is, I was gonna show on a map that the Great Pyramids are in Giza, and Luxor is where King Tut's tomb was found, and most of these tombs
Right.
is the Valley of the Kings, which is like 300 miles south of it
Yeah.
on a map.
Well,
So
the pyramids probably aren't even tombs. I mean, the idea that they're tombs is just. I mean, everything they can't explain is a tomb.
that,
Basically,
well,
it's a tomb or a temple.
they talked about as the extent of the mastabas, and there's all the nearbys, um, that these mastabas were were tombs, and that eventually they built a mastaba with a mastaba and a mastaba on top of it. The first step pyramid is the oldest, and I mean that's the way I was taught and learned it in my
Right.
class that I
Actually,
took on it.
the geology actually doesn't. The geology says that the shittier step pyramids are actually younger.
So here's where all the like crazy tombs. Most of those tombs were found in Luxor down here, and this is Cairo. This is like up here is where the pyramids are, right outside of Cairo. So they're
Yes.
quite a
Oh
ways
yeah.
away. Um,
Yeah. They're way ways away, and I mean, obviously Egyptians had beautiful, large, extremely luxurious tombs that they buried their notable people in. But the pyramids, the Great Pyramids anyway, nope.
so
There's
what do
no
you think
evidence of
they
it
are?
except I don't know. That's my answer.
Yeah.
I don't know, but I don't think they're tombs.
What about all those
Because
shafts they found and that like link up to star constellations? Do you think it was like an observatory?
I mean, we could speculate. Do you want to speculate? I mean, I
Yeah.
think that there's a couple of plausible ideas that have yet to be genuinely explored. One of them is it's an observatory or an initiation, a spiritual initiation chamber. Um, Another one is that it's some kind of energy focusing device, and that's an interesting one. It's a little out. It seemed a little out there until I looked into it. It turns out that pyramids with the same dimensions as the Great Pyramid actually do focus energy. There actually is a nano material that's made from little tiny pyramids that's used to focus energy on a nano scale.
What's the
Um,
angle on the pyramid, you know?
I don't recall. I don't recall.
What else is interesting is that an entomologist in Russia, I forget his name,
So it's like,
supposedly did a lot of research with scarab beetles and a few other beetles, and found that there were microstructures on its wings that were basically pyramid shaped and had identical proportions to the Great Pyramids of Giza.
It's by the way, it's 51.5 degrees.
51.5 degrees. That's interesting.
Not only that, but the Great Pyramid is eight-sided, not four-sided. So
Eight-sided?
yes,
Yes.
look up eight-sided
Yeah,
Great
it
Pyramid.
doesn't have a little. It has a little. It changes angle at about a certain way up, right?
It has a 4 foot. Okay, now think about this. It's 4 feet out at the center of each face.
What's
In other
interesting
words,
is that all right.
4 feet
So
in, I should say. 4 feet in at the
so
center of each
you
face.
said it was 52 degrees, about a little over 50.
51.5.
That's interesting. 51.5. That's pretty close to what Brewster's angle for air-water interface is approximately 53 degrees, which is interesting. It's pretty close to that. I was just trying to think of like constants in nature that might like be close to that, and I thought someone mentioned that it's the same as Brewster's angle, but it's not quite.
Well, also, we don't know what it looked like with the capstone and with the whatever it was sheathed with. Supposedly, it was sheathed with white stone, and so it was flat on all sides. And then there are not terribly well confirmed, but fairly interesting references that it seemed to indicate there may have been mica sheets on a
Yeah,
part or all of the Great Pyramid.
which is of course a waveguide for certain frequencies of electromagnetic radiation, right?
That's true. That's true.
So yeah,
you know, who knows? It could have been an energy.
right.
There's
And,
a
Chris
there's
Dunn.
a there's an sorry, go ahead.
There's a book by Chris Dunn, I think, called the Giza Power Plant. I read that before one time. Someone showed it to me. You got to read this. So it was short enough, and I read it. And that was one interesting theory on the technology of the pyramid and some of the create more outside of their ideas on what it was really used for anciently. Of course, he had this whole idea that they mixed up, grapes and like and to create like basically hydrogen gas, like they used a chemical reaction in the Queen's chamber below that subterranean chamber to create a hydrogen gas which would flow up into this other chamber, and there was this resonator hall with this microwave signal that.
I'd like to
Oh,
make
you're
a
real
correction.
quiet. You're real quiet, Sebastian. I can't really hear you about that one. You're in the
I'd like to make-
background. You're real quiet. You might have to. Mike is an
So-
insulator, right?
Micah, can you hear me okay?
Yeah.
Yes.
Okay. Micah is mildly semiconductor. But anyway, I just checked, and
They can't hear you. I can hear you a little bit, but they can't hear you. Sebastian, do
Yeah,
you
I
want to
can't.
do you want to jump on Skype so you could be the same? I'll invite you to
I
this
would like-
Skype call. That way you can we'll be the same volume. All right.
I would like to
I
make
had,
a correction. Can I make a correction real quick? This is interesting.
Yes.
Yeah.
The actual angle of the Great Pyramid is 51.42857 blah blah degrees, which is 1/7 of 360.
Oh. Okay, so incredibly precise.
Incredibly precise. Yeah. And I believe it's out of true north by 5. I don't remember. Wait, how far is it off true north? It's actually an interesting number.
Right. Yeah, I remember reading something about all these interesting facts about the pyramid, but
Can you guys hear me now?
Yes.
It is-
Awesome.
Oh,
Awesome.
it is. There it is. It is 3/60ths of a degree.
Yeah. The pyramid is like one of those guilty fascinations for me. I've read way too much about it, but like in terms of what it looks like to me, it looks like a mechanical transducer. I mean, it's tuned to the Earth's frequency. It's got all the right elements in to be a mechanical transducer. It's got tons of quartz crystal and as the granite. It had limestone covering to act as an insulator. There was water that was always kept around it, as well as a stream that flowed under it that had a gravity ram pump that ran all the time when the thing was going, and that would produce a drum beat, that would produce a heartbeat. So that would create a frequency that would be reflected upwards into the pyramid. The thing was clearly a mechanical device. My theory is that it was, or my crazy out there theory is that it was some type of ionosphere, like ionosphere strengthening device for the last pole shift. That's my theory. Is that at a time when our poles were collapsing the last time around and the sun was starting to flip out, this thing was turned on to keep them safe. It's the best I can come up with, given what I see.
And all this resonative inductive coupling is awesome. I wish Jeremiah was here to tell us. Like he broke it down Wardenclyffe Tower, and I was explaining how that all worked and in terms of the same exact thing, and it was rather fascinating. And I definitely wish more research was done on this sort of stuff. But it's again, a lot of the research is being suppressed or guided by people with I don't know. It's unclear their objectives.
I don't know, but I think ultimately, like,
Securing funding for themselves, and continuing make sure that the funding doesn't stop for themselves.
Well, I mean, what's really fascinating is that we keep getting hammered. Oh, you can't go faster than light. You can't go faster than light. It's the cosmic speed limit because Saint Einstein said so.
Right.
Because relativity and gravity. It's like, well, looks like relativity is about to get dethroned by the sapphire.
That's pretty amazing. I mean, the elemental compositions that they. When I read the report, I was just like, what? They did
experiments based on Velikovsky's model of electric universe theory?
No. Yeah, I mean, sort of. That's yes, but all of these guys were inspired by Velikovsky.
Got it.
What they did was they used Birkeland's model of the sun, and created a Torella in a vacuum chamber, but highly controlled.
Yeah.
And then they did a whole bunch of experiments in that vacuum chamber. And I was blown away when there were a number of things that happened, which you can go and look at. But the thing that blew me away the most, there were two things. One was the fact that, as was just mentioned, they actually produced lanthanides. And I mean, there were the materials of the Torella, the metallic materials, were transmuted.
Yeah.
Into a wide array of substances, including lanthanides. Interestingly, they didn't mention uranium or plutonium, but they mentioned a few others. So, and then also what happened was they mentioned a repetitive event. It happened twice. They actually tried to make it happen, and it did, where the amount of energy that was being produced by the Sapphire Project Torella was more than the energy being input.
Mm.
And both of and that happened twice, and each time it happened very quickly, and they were unable. The first time they were unable to control it, which it melted the electrode in the Torella, so they pulled it out, and that's when they found all these elements had been created. So what they're assuming, I mean, obviously what we could assume is that they achieved some kind of fusion.
Yeah.
Wow. But they weren't going for that. They weren't trying to make fusion. They were just trying to make a model of the sun.
So
well, that's
another
assuming
thing.
there's fusion. Perhaps
what's the
they tapped
consensus
into
here on that anyway? Electric universe theory. What's the consensus with you guys? What do you guys think about that?
There is no consensus. Consensus is a spook.
There's no consensus. I think. Let me say that I think there is compelling evidence that, at the very least, the plasma cosmology elements of EU theory are real. Not only real, but possibly more real than what we think we know with the rest of our science. Right. And that's not actually too spooky. It actually just means that our models are off in terms of how we think things form and how they manage. But what it does do is, as was mentioned, it removes the need for the relativistic explanation of gravity completely. Because the reason Einstein created the space-time curvature, blah, 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 all of that, was because of the question of the three-body problem. Meaning, if you only have an attractive force and you have more than two bodies, the system becomes chaotic, inevitable, and very quickly. Right. So, and there's no way out of that. So he created space-time and added it on and said, well, there's this curve, this curved space that's acting as a sort of waveguide through which the planet drags itself, and that's the stabilizing force for the orbit. Now that works mathematically because, of course, you look up in the sky and you make it work mathematically. But with plasma cosmology, the theory is different. The theory is that the sun is gravitationally attracting all the bodies, but it's also simultaneously electrically repelling all the bodies. And so there's a balancing force.
Right.
And it's related to the... Sorry, go ahead.
Isn't that kind of what we see in terms of how our planets are placed in their orbitals too, in terms of
That's why I say it seems. That's why I say it seems more compelling, because things make a lot more sense then. If you look at the orbits of the planets, like, oh, okay, so essentially the distance of the planet away from the sun is not only dependent on the gravitational pull of the sun and the mass of the planet. It's also dependent on the charge on the planet, the mass. Basically the entire charge on the entire body, which is the repelling force. And that charge is being supplied by the sun. So it's an interesting, and it makes sense. It makes sense, right? I mean, lots of things start to make more sense, at least in terms of intuitive observation.
Now I really think my pyramid idea might be closer, because there's so much we don't know about the sun, and clearly if we found lots of evidence for all kinds of extremely fast particle exchange between the sun and our planet through these like helical magnetic.
They're Birkeland filaments.
Okay, got it.
Yeah, I mean that's not what NASA calls them, because they don't want to acknowledge that there's actually current flowing into the Earth from the sun.
So these Birkeland filaments are basically channels that end up being informed by the motion of these high energy particles from the sun, but they tend to come in fine streams.
Essentially, so imagine a couple of charged particles coming near to each other at a very high rate of speed.
Okay.
Most of the time they won't collide. What'll happen is they'll deflect each other. So their trajectories will deflect each other. And then, so if that happens enough, what happens is they start orbiting around each other, and you end up with a tube. And then what happens after a tube of charge that's spinning in current, a little bit of current, a little bit of magnetism, and then over time, and that attracts more particles, and over time that creates more electricity and more magnetism just through the kinetic motion of the particles in space. And over time you get an electric field and a magnetic field, and the tube turns into a pair of filaments.
And how far do these filaments reach? Do they go actually all the way from the general field around the sun and reach to the Earth, or are they generally just around Earth following its own magnetic field lines?
We don't know. We know that the quote unquote magnetic ropes.
Well, there should be a portion of them. Right, the Earth's own magnetic field kind of deflects a portion of, a large portion of that from the sun, right?
No. Hold on. This totally transforms the idea of the Earth's magnetic field. The Earth's magnetic field might be dependent on the current that's coming into it.
It absolutely is, yeah.
So what that means is, anyway, these magnetic.
So if the Earth's like a diamagnetic, or something that creates its own magnetic field in opposition to the externally applied field.
It's kind of like I think the theory used to go something on the lines of the Earth is ferromagnetic, and even though it happens to be in a state that it's not capable of being ferromagnetic, there's just enough cooler material on the planet where it happens to have a magnetic field. And now research goes something like
super weird.
The field is actually caused by the external currents flowing into it, and even though it is ferromagnetic, it's not self-sustaining magnetic. It requires the current flow from the external environment.
The first thing you have to do is remember. Okay, so. The standard model of planetary dynamics in terms of the magnetic field goes like this. Inside the planet is a big giant sloshy core of material,
which of course is ridiculous.
It's called the dynamo, and that's the standard theory of the magnetic field. Now, with a Birkeland filament attached into the Earth's essentially attached to the Earth at the North Pole electrically, you don't even need that. The entire magnetic field of the Earth could be coming from that filament. All of it could be being induced by that filament, just like an electromagnet.
Mm-hmm. Well, it could be, but the only problem I'd have with that is that the magnetic field of the Earth fluctuates along the precession of its axes, which isn't exactly pointed at the sun all the time. It's slightly off. And so this would indicate that there is a hysteresis, if anything.
It doesn't. of course there could be hysteresis, but it doesn't have to be. The Birkeland filament is made up of gas, so it doesn't. It's not something that won't move as the Earth moves, right? And we don't know much about it because it was only discovered, what was it, less than 10 years ago, if I'm not mistaken, right?
Correct.
Wow.
And what's weird
Yeah.
is that when what we're finding out is that there's actually a bunch of different essentially layers. So you have it's not just like a magnet where you have positive going inside and negative going out one
Correct.
side. As it turns out, there's a
Multi-layer.
bunch of positives and a bunch of negatives going in both sides, and then there's also equal.
Imagine a ball, and then how do I describe this? Imagine a ball with a lot of very shallow coffee cup handles all around it symmetrically. Those half toroids are all around the Earth right now, and those are plasma toroids. They're in dark mode, so you can't actually see them, but they've been detected and measured. So those are flowing in. Yeah, and those are flowing in weird directions as well. So the structure of the electrical environment around the Earth is actually a hell of a lot more complicated than anyone ever thought it.
It sounds like you could have like hyper complex plasma structures in space given the right environment, like self-sustaining, Wow, I wouldn't be surprised if there's some type of like potential for life out there in space with something like that, because those structures can get really complex.
And when we get into panspermia theory, and we know that mycelium spores can indeed actually, just from Earth, a lot of mycelial spores are so lightweight they can actually reach up into space and even be swept away. So,
yeah, actually, there's a rough number somebody has. I forget how many. It's in the tons. How many tons?
It's a substantial amount, like enough to make it to interstellar space. Potentially, if these things live for a long time. I mean, look at tardigrades; they live for quite.
I'm sorry, but I can't find it right away here. But I do know that millions of tons of spores are released in the atmosphere every year, and that some fraction of those millions of tons makes it into the upper atmosphere, and they're so light and they're so responsive to electrical energy.
They can be lofted right up into space.
Yeah, they eventually end up. Yeah. They end up in space because of, it's thought because of the Van der Waals force. Because the Earth is rotating.
NASA did a whole bunch of studies on this on asteroids and meteorites. What they were looking for is the effects of high energy particles and electrostatic forces causing lofting of dust on the surfaces of planets, and also causing ejection jets on smaller bodies flying at high velocities through space as their electric field changes in proximity to the surrounding spacious medium. So I think it was kind of interesting that the NASA paper basically does say that there is plenty of evidence that lofting occurs for even space dust on things like the surface of the moon when electrostatic charges interact with it, and that they can be sent up at thousands of miles per hour in some cases following these electric field lines.
Yes.
And the electric universe theory attempts to explain all this too, and they're one of the ones that talk about this. There was a lot of problems in that model. That's my opinion with it. I know I just got into the chat when somebody was asking about, what do you guys think about the electric universe? Anyway, there are problems with the model. It makes a lot of very good points, and I would recommend that people look into it surely because it makes you think and it makes you ask different questions. Like, does gravity really explain taking? I mean, we already know electric charges. Go ahead.
Who's to say that gravity itself isn't a form of electromagnetic force or some other?
Well, I would make the argument that it is, but that'd be, that's the highly negotiable point. I've always.
I don't think it is.
Saint Einstein can't be wrong.
Well, I think, according to Wolfram's theory, it's a shrinking of the grid that's caused by mass. It's very similar to how it works in general relativity.
Yeah, and Jeremy Higgs discovered a boson too. Yeah.
The Higgs boson.
The Higgs boson.
Oh God.
Like I can't tell you with absolute certainty that natural gravitation is caused by nothing but electric charges. What I can tell you is that you can basically synthesize something which acts exactly like natural gravitation using nothing but electric charges.
Yes, you
Well,
can.
So,
There have been lots of people who've done it over the last couple of centuries. One of my favorites is actually Victor Schauberger, right? The water wizard, if you guys have heard of him. You know, who
That
studied.
guy was brilliant, but I still do not understand how in the world
I don't think he created
some of
anti-gravity.
his discs were supposed to produce
The only
propulsion.
thing I can think of is the model that I remember reading about was essentially they talked about something like an atomic low pressure zone. Essentially, that vortical motion acted as an ordering force on water that dropped it down towards its anomaly point of 4 degrees centigrade. So the vortex itself, basically in a closed system, somehow or another would cause this zone of atomic low pressure as the vortex ordered the water that then came out the other side and was like somehow or another shed its, I don't know, extra energy or something like that. But
Yeah, I mean, a thermal energy converter is absolutely
that's a valid
interesting thing.
device, but I don't know how it's going to get you straight up off the ground. Other than, I don't know, like maybe there's stuff about water we don't know. Like I personally find it fascinating. We're learning new stuff about it all the time, and
There is one thing that you could say maybe about water, and you could go as far as to stretch this argument to say there's enough energy in atmospheric water to continue this idea, but it's that water has an easy zone, making it, a four-state type of water.
Yeah,
So
you're
water
talking about
without a
structured
charge.
water.
Right, exactly. So if water can absorb photonic energy in the IR and the UV spectrums,
right.
and it can hold on to that energy, then that means water is actually like, in a manner of speaking, a photon battery. It changes states and it starts to structure itself. So you can destructure it and extract that photon energy that it absorbed. Of course, there is some kind of power there.
Victor Schauberger was all about keeping his water in the dark for it to keep its like properties. He built this log flute that was like unheard of in terms of how well it worked, because it was able to get like logs out of like deep old growth forests that nobody else could, and he did it
all the way down the mountain, exactly.
Right.
And it would just do it without them ever jamming up or blocking or anything like that, because of the way that it flowed. But the other thing that he noted when he was talking about his design is he made point to note that you should be aware water changes its flow and its viscosity as it changes temperature, which is something that we generally don't think about.
Yeah, well, that's very true too, and that's how his engine worked. Is that like as water dropped down to 4 degrees centigrade, it increased its laminar flow, thus becoming denser. Thus, because it became denser, it like drew the less dense water that was behind it into it in a suction instead of like as an explosion. So I mean, it all kind of sort of makes sense from if you think about it from that perspective, and there might.
But then that still leaves us with a big question about Schauberger, which is not. I don't think there's really any question about the fact that he was a genius or that he had figured out the most efficient way to work with water flow in natural systems. The big question is, did his machines actually produce enough? Force using what is conventional technology, that's Venturi forces and surface friction and various.
Does gravity flow like water, and is it even a relation? And then how did he do it if he did? Like
I don't know.
How does this device produce a force?
So
gravity is an incredibly weak force. I don't think Schauberger had to worry about gravity much. I mean, when you talk, to be honest, just the fact that completely forget the engine. Like, let's just assume that's not what we're talking about. We're just talking about his discovery of how to flow water through a structure without that water touching the sides of that structure. Using wood. That's unbelievable. That's an unbelievable
I don't know if I'd go
accomplishment.
as far as to say it didn't touch the sides. I mean, water was still in contact with the sides. It's just that there was really no velocity of the water at the point where it meets the sides.
Was
a way to eliminate the surface drag?
Well, his contention was that the water.
I don't remember reading any papers from him like coming up with like a calculated angle for how to angle the boards. Like I remember seeing like I remember seeing this diagram, but it wasn't like super technical about it didn't go into like.
But it's just too hard to reproduce. Like I love his stuff and I love the ideas, but it's like to reproduce those curves and figure all that out is a lifetime's worth of research and like I wouldn't even know the theory behind it. Like that's what I just want to know how
Well,
it
don't you think
works.
it was like trial and error? You know, they try. He had
It
this
is.
idea. He had an idea for how to make these log flumes, and then he just had to like tweak them until he got it right. You know, but
He was a naturalist, right? So he spent like 10 years he grew up out in the forest alongside streams. So he learned by watching his environment. You know, back in the day when nature was still like super duper awesome, like
when there were
there
still
was
huge trees, you know, 1,000-year-old trees everywhere until they cut them all down.
actually looks like Pandora here because that's how it was. That's what pisses me off. Like people look at movies like Avatar years ago and like pine for Pandora. But the thing is that our planet is exactly like Pandora. Like even down to the mycelia in the ground. Like I don't know if you guys have seen, you know, Fabulous Fungi, but that movie will blow your mind. If you haven't, go see that documentary. It'll be like you'll be so glad you did. I made my daughter watch it, who could barely get off her iPad, and she was like ecstatic for a whole night after that. It's that because it shows you how like prevalent my mycelial network really is. It goes everywhere. Like there's like 300 miles of mycelia under every footstep when you go to like even like a.
I watched that TED talk on slime molds was freaking amazing too, about the things that they were doing with them in the lab.
Yeah.
Well, you know, I'd like to, you know, just emphasize here that people, humans, as you know, in general, academia and people have their head really far up their own ass. They think they know everything, when in reality, both collectively and as individuals, we know so little, we can't even begin to fathom how little we know. There's so much out there, and we have all these dogmatic, axiomatic assumptions that we ascribe. You know, if you were to tell somebody that there's evidence that contradict the existence of black holes, and the evidence for black holes is more flimsy than what academia is touting it to be, people will look at you like they just seen a ghost, like you're crazy.
Yeah. Who are you? Who are you to say that? It's like, well, here's the evidence. You know. Like, I mean, the only reason we think there are black holes is because there are energetic events that occur in the universe that cannot be explained except through something like a black hole, if you believe in a gravity-only theory.
Right.
Well, this is also the.
And I just don't think I'm not so sure I believe in singularities. I just don't. I know that's what I've been told my entire life, but like
they're fairy dust.
Where does it go? Math is a thing. Like it doesn't go. It's information. It doesn't just disappear or collapse down into itself. Like you can compress information down to a certain point, but not any further. And so where does it go? Like
let me ask. I'll ask if you.
Can I just
ask if you? Sure, go ahead.
Chime in with the whole thing about black holes, and you know, because they didn't just come from we've never actually seen a black hole. We've kind of got that first image of one that we created through all the data we took. We're just looking around the black hole to try and get a visualized image of it. But I believe I was like, you guys are wrong about where the black holes came from. It actually right after the theory was published of theory of general relativity. It was a German astronomer named Karl Schwarzschild who calculated one of the first exact solutions to the Einstein's general theory of relativity and came up with the Schwarzschild radius, and that's sort of what came up with the fundamental theory behind black holes.
That's actually a problem, because the Schwarzschild radius isn't a radius; it's a Gaussian curvature. It's just called the Schwarzschild radius, but a Gaussian curvature isn't a physical limit. A Gaussian curvature is a pure. It's essentially topological. It's a differential geometry term that's used to describe.
You're talking about a normal distribution.
Yes. Well, I mean, Gaussian curvatures can be used. They can be superposed. That's the point of it. The Gaussian curve can be superposed into any geometry. That's the whole point of it. Their geometry Yeah, go ahead.
Go ahead. I was going to say, you can even impose Gaussian curves into Hilbert spaces. It's crazy.
Sure. Gaussian curves are specifically designed to be independent of their embedding space. But what that means is they prove nothing about the embedded space that they're in. Like they don't actually give you any. So in other words, they're just a description of something that you can then use to manipulate some object in an embedded in a space, in any differential geometry or algebraic space. But you can't. But it's you can't go the other way. You can't. There's no. You see what I'm saying? So
Well,
the Schwarzschild radius, the general solution that Schwarzschild came up with, was assuming a few things. It also was nonlinear and didn't actually like his solution. His original solution didn't actually. It wasn't actually linear, so it couldn't come. That's why ultimately Hilbert and Einstein and a number of others developed the theory around developed parts of the general theory to compensate for that, because they wanted it to be solvable. They wanted parts of it to be solvable anyway. Nobody uses the original Schwarzschild formulation anymore because it's nonlinear. It's not really solvable, if that makes sense.
Mm.
And the data that they took to supposedly photograph that black hole is largely a matter of interpretation, because a lot of people, a lot of scientists and cosmologists and etc., would just look at that and go, well, actually, that's just a plasma torus. Nothing out of the ordinary.
Yeah, and that's what I was going to say earlier was let's look at it this way. All the evidence for black holes has to do with observing the motion of bodies in space and energetic outbursts of space. That's all the evidence.
right.
They say there's gravitational lensing, but you can't really prove it because you can't measure before and after to prove the lensing ever occurred and so on. So it's not really a proof.
Yeah, right. We went from talking about pyramids to black holes, man. Yeah, so this is kind of getting outside the blocks of what we were originally kind of going after and stuff.
Can I just-
By the way, I
Well,
completely
let
missed the
me-
first hour of
can
this
I
show.
just-
What were we talking about in the beginning of the show?
In the beginning, I was talking more about this fundamental theory of math, and I was trying to talk about some experimental, how we look at the universe and what we have to kind of model and copy after. And we were getting into the periodic table of elements, some interesting things about geometry. We were talking about polyhedral combinatorics and how different polyhedra can explain a lot of the interactions we see in quantum physics through the Garrett-Lisi's E8 model and the certain rotations in E8 symmetry which look like particle interactions, and why that's why that works.
Do explain a lot.
Why that works and why it might, kind of how it works and how it might fit together as these, not what Feynman would have called the six not so easy pieces of the puzzle, which we're trying
the thing that I want to emphasize is that if you're trying to harmonize math and cosmology, you're going to need a good cosmological model first.
Well,
cosmology.
Sorry.
That's sort of the idea of extrapolation, versus introspection. We're trying to build it from the ground up. Is to start with the most basic concepts and build something that will eventually, after a million, 10 to the 500 iterations, produce something what we see from cosmology or something. Well, of course, there's no computer that could ever calculate it or within our lifetimes show us the answer that our answer is even correct. So it's almost like.
Yeah, I'm personally interested in finding a simple looking at very simple simple philosophical concepts like self and other, 0 and 1, and using and taking those and recombining them with themselves and rotating the results of that and doing very simple iterative recursive actions, right? Something that would is very simple, basically the kinds of rules that you would run to run a cellular automaton. Essentially, is there a set of rules that are very simple that use very simple concepts that produce and tumble out some of the kind of the fundamental ideas or properties of the forces that we see in nature. If even there's a model that even hints at general behavior of all the fundamental forces in it, even if it's not doesn't describe reality, that's still interesting, because that tells us something about the nature of how things are put together.
And I like a couple things that we just to summarize real quick for people what what kind of we've come to conclusions about certain things. But nothingness. The concept of nothingness is like a super important piece of this puzzle. It's sort of a central idea. There's a book I read called The Hole in the Universe by Casey Cole. Very interesting, extrapolation on all the philosophical idea, of the just all the philosophizing around the concept of nothing and nothingness, and how all the laws of physics that we see are conservative in nature. That for every action there's an equal and opposite reaction. We have general relativity, all these things seem to derive from the idea that that nothing existed at the beginning of the universe, and that nothingness is somehow conserved through whatever's happening at every point and step in time. But yeah, so we were trying to create a universe from nothing using these simple mathematical rules, and trying to run them within Wolfram's model to see what we could come up with, and and learn a little bit more about these basic building blocks and how they might fit together. But that's where we're at, and it's not an easy puzzle. There's a lot to it, and
so far I've got our grid cell here. I've got the algorithm that creates kind of this target grid cell I want to play with. Now I need to look at that algorithm and figure out how to make it essentially turn that single grid cell into multiple really quickly with, or maybe, I don't know, I'll have to see how many iterations it takes, but essentially now is find the most elegant model that turns this one cell into many, right? Because I was able to turn nothing into like a three-dimensional, like nine-noded structure that's like doubly connected. That looks really interesting from my perspective as somebody that likes to play with cellular automata a lot. So I've been playing with a cellular automata probably for like 25 years since I wrote my first one. I think when I was like 16 or something like that.
Oh, so you like Emergence?
Oh, I'm fascinated with Emergence. For me, it's everything. It's what's happening everywhere. It's what accounts for everything that we see. Right? It's just like everything has its own kind of way and its own behavior and its own purpose, and it's fascinating to see kind of that landscape of possibilities. That's why I'm a big fan of Wolfram's, and that's how Jeremy and I just connected. We know each other for a bit, but we connected again after Wolfram released his latest, because it's just, I love it, and he's, he thinks it's the right direction, and I think it's a really interesting direction to study, the fundamental laws. I think there's something there, even if, like I said, even if it's doesn't tumble out the numbers. Like I'm not sure who was talking about it. Somebody was saying about you can't just fudge your model, make it perfect just because you think things are perfect, and reality is telling you that there's a little bit extra, or it's just slightly off. No, it's slightly off. Deal with it. But people can't handle it. But it's like it's I don't even know what I was saying before that, but like this stuff is fascinating to me, because I think there's something interesting there to see about it. If we can see how things relate to each other, like the force mathematically relate to each other, even in a simpler model, maybe that's a hint for how we can get somewhere with this.
I would have to agree with the emergence theory thing too. Whether Wolfram's correct, whether the E8 model is correct, they all basically suggest the same idea, that all these forces that we think are the constant end-all be-alls that regulate the rest of the universe are actually emergent from the properties of the universe that lie beneath them. And they're not particle properties per se. They're not properties of motion within the conventional three dimensions that we're used to, but these things come from outside of those dimensions, and then they interact, creating this one. And I think they all kind of come to that same conclusion in many different ways, mathematically and through models. I am a huge proponent of emergence theory in general.
Yeah, they're like it's like the forces are geometrically like balanced in some dimension somewhere, and it like forms a sound structure, right? So it's put together well. Right. It fits, and so the forces are what they are, and of course they look right to us. How could they be any other way? Well, of course they're right, because it's it's on this higher dimensional structure that is put together just perfectly. There might be a zillion other ways of putting it together that would work for a different universe that would be stable. The fundamental forces might be completely different, but it might still work. That's possible. Why not? But here we are.
Well, if the fundamental forces of the universe are emergent, that means that on some level they're not computable, meaning we have no way of playing the clock backwards.
Oh yeah, absolutely. We can understand
No.
emergence if we understand the
No.
angles that things interact with.
No. That's the definition of emergence. You
But-
can't go backwards.
Okay.
If you don't have the original, then you can't go back. You have no way.
Yeah, you're
of
basically
knowing.
still saying that the original is unknowable, and that I would agree with.
Unknowable. It is that's the definition.
Yeah, the information going back in time comes encrypted or like unresolvable, kind of.
Right.
Yeah.
Depending on the rules, a system is either going to be rewindable back in time, or it's going to be computationally irreducible, and it's not going to be able to be rewound because the rules are creating a new state that just isn't. It cannot be. The last state can't be extrapolated from this one based on the rules, right? So yes, but nonetheless, it doesn't mean that
If you don't have the rule, that's my point. No. My point is, if you don't have the rule set and all you have is the structure, then you have no way of knowing if what you just rewound is the actual thing.
I agree. But what you can do perhaps is find structures that are similar in some of the forces they exhibit, or the relationships between those forces that help us further, get further with things, here.
You can definitely look. Don't get me wrong. You can definitely find out very useful things.
Yeah.
But I'm just saying.
So the idea is creating a model that produces useful predictions that lead
Right.
us to a good direction where we're
In the future.
now. So basically, if we can create a puzzle from this Wolfram thing that produces hydrogen and all the other atoms and their spectral emissions, and we can get all that, we can show how to get all that stuff, and then it predicts something else new. That would be really cool, but. It would have to predict everything that already is, to a T. It would have to predict all that other stuff that we already see, and all the things that we can agree upon anyway. Maybe some of this other.
Yeah, and
other
to
theory.
do better, to have to predict those things more accurately than the current models that we're using.
Right. So
Yeah.
the things we don't agree on gravitational waves from LIGO and everything, but we at least predict the stuff that we can really agree on, like a periodic table of elements and chemistry and well proven and well known defined laws of the universe. And
Well, the good thing about LIGO is, when we do perfect our gravity control technology, all we got to do is sit wherever we're at and just aim it at LIGO through the Earth, and it should be able to pick it up. So.
Yeah, that's true, right? So if we
Don't
ever
ever
succeed,
have to go on site.
if we ever did succeed, right, that would be great.
The thing about I lost the thread. I'm sorry. You guys started talking about LIGO.
We're talking about just affecting it being able to pick up any kind of gravitational anomalies, and us, sending those things straight through the mass of the planet because it really doesn't matter in that case. So you don't have to move your lab or take the experiment to them. You can just do it wherever you're at and make sure you aim it right.
I know what I was going to say. When you start talking about defined laws, all you're talking about is a model that works most of the time.
Right. I mean, that's all we can really ever hope for. We're just monkeys running around Earth and trying to understand what it is that we see. So I'd say that's pretty good. If we have a model that works most of the time, I'm happy with that.
Yeah. But the thing about an interesting thing about chemistry is that quantum theory has shown us that all chemistry is actually, there's a lot of quantum interactions going on in chemistry. So although the models we use for chemistry work pretty well, do you guys know about? Okay, so any kind of quote unquote chemical interaction is actually hopelessly irresolvable in terms of its actual total number of permutations that are occurring at any given moment. What you can do with chemistry is you can you can make a prediction, perform an experiment, and get a yield, get a result. And the expected yield is going to be X, and you're not going to get X. And so, like for example, if you wanted to synthesize something, and you say, well, I'm going to try and get a yield of 50%, and say you end up with 30% yield, which means your final compound that you just what happened to all the other stuff. And you do back analysis, and you look at the actual, the process as best you can. You figure out all these other side elements that are being created, redox reactions, side reactions, ionic reactions, all these little things that are happening. And then you tweak your process to improve the yield, to eliminate as many of those side reactions as you can.
Yeah.
You never get to 100% yield ever, because there are limits. And,
Right.
and all I want to say about that is that we have no idea what those limits. We don't have any real idea with any precision what those limits are. We can sort of predict what will happen in a new reaction, perform it, and then something will happen we didn't expect, and then you see what I'm saying? So, and then over time, through testing and experimentation, we figure it out. But it's the original prediction it never results in the expected yield ever, and it takes time to refine the process. That's why, synthesizing a drug takes so much time and effort. It's pretty straightforward when you look at the process of synthesizing a drug. Oh, you just do this, all these steps. But how did they figure that out? And they figured that out through lots and lots of experimentation. Oh, the temperature has to be so much during this reaction, then we have to add this other reagent, so.
No, right. It certainly doesn't come out of the computer as a instruction that you follow.
Correct.
It's a lot of trial and error. And another interesting thing is that even once you've figured out the methodology of the process, sometimes the process changes spontaneously for no reason.
Yeah, that's a weird thing.
You mean like the speed of light did when we were first trying to figure out what that was all around the world?
Well, but chirality. When you synthesize. Sorry, go ahead.
Chirality in molecules is huge. Is I thought that was one of the most interesting things I learned about, is that all the proteins in your body are right-handed, and that if you ate an orange that was all left-handed proteins, your body wouldn't be able to get any nutritional value from it. It'd be like the perfect diet food if you could somehow like genetically like reverse the entire chirality of like DNA to start creating left-handed protein plants, so that you could just sell like apples that didn't do anything, like that tasted like apples but just couldn't be processed by your body, but then they might do weird things too.
I have to wonder if it would actually taste like an apple at that point.
At that, what would happen
because the sugar would be left-handed too,
right?
So how would it
well, would it be? I mean, a sugar's not a protein, so how can you have a left-handed sugar?
So hold up. If you make an entire human that has left-handed chirality, would that create a whole new set of racial problems?
Maybe.
Well, if they starve, probably, right? Unless we grew some left-handed food for them too.
That would be strange.
Left hand sounds like an age-old problem.
But what ends up happening? So if you look at like dextroamphetamines and levoamphetamines, so whenever they're producing these chemicals, they have to separate them using spinning chromatography machines.
Yeah.
And sometimes what happens is that it will start producing different ratios, and which is fine, because then they just look at this machine, the machine and the instruments and the measurings and the various etceteras. It's just out of calibration, got to recalibrate it. But then other times, it's not the machine. The procedure is doing just fine. And all around the world at the exact same time, all the machines have to be retuned because the laws of chemistry changed.
Some fundamental property that's changed. There's a guy that tracks the fundamental properties of physics, and I don't remember what his name is or his website, unfortunately, but I saw some video about him, and he tracks all of this. And apparently, he's seen variations in in the speed of light and a few other constants, which to me come as no surprise. Like I actually do believe that there's going to be some variance because there's some shit that we don't understand yet that we're not accounting for in our standard model.
It's not just a matter of stuff that we don't understand. We just axiomatically assume that there are unchanging cosmological constants in these anthropocentric laws that the universe must.
It makes it feel better, right?
Yeah.
So does NIST keep track of all this stuff?
No, they've redefined the speed of light in terms of the meter.
Oh yeah, that's what they did.
They've created the rubber ruler phenomena. So
that is exactly the right term.
Yeah. So before the 1960s, I believe it was, the meter was tied to the decay of krypton, a specific isotope, and I forget what it is off the top of my head, but I digress. And then because the speed of light kept changing uniformly around the world, depending on the time that you measured the speed of light, they said that doesn't work with general relativity. St. Einstein can't be wrong. So instead, we're just going to tie the meter to the light. That way, the speed of light will never change. That's an egregious oversimplification, but
right.
Well, yeah, basically that's what it comes down to. The speed of light was a consensus agreement that wasn't actually a measurement that was found and discovered to be.
Yeah. And at the end of the day, right, like it's not like a big conspiracy either that people are like doing all this. People are just lazy and like don't want to like bother to change something, or they have their reputation riding on some measurement or something like that, and they don't want to change it.
A lot of what it is that these academians tie their ego and their legacy to their theories and their models, and if something is about to upset their model, it's almost like they'll take it as personally as somebody that's trying to end their genetic legacy. It's very strange.
It is it's protective. It is like a parental type of protective reaction. My baby can't do nothing wrong.
Yeah. Yeah, well, when you've invested your entire lifetime, and so much of your time like learning all this shit and believing in it, it's a lot to take to have,
It is. Well, and
that's again back to
science. There's so much unscientific behavior among scientific people. If you're really a scientist, then your whole lifetime is spent trying to accomplish being more accurate, being more correct, understanding better, which means that the whole process is a continuous series of changes that your model and your understanding goes through.
All your axioms, all your facts and your axiomatic logic system should be regarded as potential lies. Like is the way it looks at it, is that no matter what you think you know and how well you think you know it, it could be wrong, and you have to like always, I don't know. There's certain things where it's real. I like pure mathematics and stuff, but yeah, you have physics is the applying it to the actual system and the actual structure, and we're finding that's not always as easy to do, and and it could go back to these axiomatic values themselves in these logic grids or these hypergraphs that could very well be. These things could very well change backwards in time too, be entangled to points backward in space, so that suddenly this thing that was relying on all these other things being true forward in time, this thing becomes not true, and then that just affects everything else down the chain, which is kind of like.
Have you ever looked at a picture where it looks like one thing, you swear it fucking looks like one thing, and you're sure of it, and then all of a sudden the whole thing changes and it's something completely different, but it's still perfectly makes perfect sense, right? I think maybe the way we've developed our theory is like that. We see the universe from a particular way, and our assumptions over time have been proved correct by experimental tests. But that doesn't mean there can't be like a half a dozen different potential ways of building up the same way of different ways of looking at the universe, like that are more. That tend to reveal more about the universe at different places because of their approach. And so maybe you can model things from the perspective that we have, where it's things are the way they are, and where we get to a certain dead end because we are like smashing particles and we don't We don't understand. We can't. It can't get any smaller. But like that, even that attitude, even the whole concept of like having to separate more and more, divide more and more, as if there's something that's going to be there, like further when you divide that. Like that whole thing, it just, I don't know. It just there's other ways of perceiving the universe that make just as much sense, but don't have that as a kind of a fun. I don't know.
Yeah, this is really cool. I mean, there's a lot of good stuff in here, and I encourage like the physicists who aren't, like, to read through all the stuff that he's written and said in this technical introduction part. To go through that, at least take the time to spend and go through that. It's really freaking cool. One of the things,
Jeremy, that's exactly what you were saying last week when you were talking about the atomos idea of, there must be some kind of fundamental smallest piece, and why that idea is not going to get us where we really need to go.
Yeah. It's interesting because what if this is going to be, we find the smallest piece, and then like Wolfram said that the proton could be a combination of 10 to the, according to his model and projections, it could be like something like 10 to the 25th of these vertices, and in which case if you need 10 to the 25th vertices just to model a proton, then what good is your model for for making calculations and real world predictions and other things, because it's just going to be so overly computationally complex that it just won't make, it's not going to be worth anything. But one of the things
subdividing is the same as the process of getting to the speed of light, right? The smaller you try to get, the more energy it takes for you to even be able to make a measurement at that level. And it's because you've got to smash, right now we have the concept of, particle smashers, which is fucking ridiculous. But
it's just nothing but like little kids, taking things apart with hammers, which is how I started. And you learn a lot that way. That's literally how I learned everything I knew about electronics when I was 6 years old. Is with a hammer. I didn't know what a screwdriver was, and we obviously don't know how to unscrew these particles either. We just have to smash them with hammers.
That's it. Our current physics understanding. We're in our adolescence, man. We're like teenagers, starting to grow up.
Yeah, I think that's given us a lot of credit.
I wish more physicists would acknowledge that.
Yeah, and the fact that particles are more and more ephemeral as they get smaller and smaller should be like a huge hint. The fact that that's the case means that the less of like a particular amount of space that stuff takes, the less it can stay coherent. So there's some structures there at play that are keeping these structures coherent, like some type of, and we can see, as we've seen, like toruses can keep together like structurally, like, so there's plenty of ways of like nothing to entangle itself with motion or flow for these things, these structures to form and build up and as they build up in size, they become more and more coherent and tangible and less likely to fall apart than little tiny eddies in a current that might, fall apart right away, kind of thing. I don't know. That's how I look at it when I think about particle smashers, because you have to like put in all the energy in the world to get to the smallest, smallest potential magnification. That's the same as like trying to get to light speed. It's never going to happen because you have to feed the whole universe into itself to get there.
Right.
Well, I think maybe there's. I think maybe based on what you were just saying, I've always had the feeling that we're essentially exhausting the atom smasher approach, the particle approach, in terms of trying to discover the underlying structure of material. Because
we've made it about as big as what would reasonably be considered huge. How much bigger do you need to make it, and is that really going to get you any closer? Because I don't really feel like CERN got us that much closer to understanding the nature of the universe than any of the other smaller accelerators did.
No, it didn't. It really did. I mean, there've been a few interesting discoveries, but the Higgs boson was
some bogus.
That was some bullshit. Yeah, that was basically just giving Jeremy Higgs a kiss on the cheek so he could have a Nobel Prize, and it was just like.
Scientists fucking party too. That's a lame way of doing it for sure. It's like, It's
Yeah,
hard
just
to
it's
get
kind of
you
annoying.
going.
But yeah, the thing is, what I think is that we need to take very radical approaches to modeling in order to find out a new way, that is better than what we're doing.
Mm.
And we would have to, of course, start by admitting that the old way we've been doing things isn't working so well anymore.
Well, it's run to the end of it's run to the end of the line. I mean, lambda CDM is falling apart. It's been falling apart for decades, but
not a lot has changed.
They keep gluing it together with fairy dust.
Yeah.
Yeah, but fairy dust is so sticky. It keeps on working.
I mean, all you have to do is there are only a couple of facts that as far as I'm concerned, doom the entire theory. One of them is the fact that every single observation we've made of comets has disproved the Oort cloud theory completely.
Yeah.
Has essentially, as far as I'm concerned, with the data that I've seen, proves that comets are, in essence, they're electrical discharge machines, not sublimating ice machines. And so that's right away, boom. So that's gone. If the Oort cloud is gone,
there really is only the electric explanation of the sublimation of ice. It doesn't simply just poof from a solid into a gas without some significant forces being exerted upon it. And where do those forces come from?
No, what I'm saying is that the evidence of the actual data being taken, they're going through huge contortions to try to make it conform to the standard model, but it just doesn't, and they're basically ignoring it at this point. But the data clearly shows, especially from 67P, that there's no surface water. There doesn't even seem to be any ice, and yet there's hydroxyls in the coma. Well, where else do you get hydroxyls? From carbonaceous materials being exposed to electrical discharge. So, like, duh. So what we have is an electrical, not a gaseous coma. I mean, the coma is...
It's gaseous, but it's electrically catalyzed.
It's electrically catalyzed. And if you... after deep impact hit, the coma changed. That was predicted by electric theorists. I mean, like, just there's so many things about comets that completely destroy the standard
and exactly
idea.
Like we were talking about
and that's
earlier,
just one thing.
Spores being able to be lofted into the outer atmosphere and up into space. The same thing happens with comets. These are just very small pieces of something, and electrostatic charges are making them move in exactly the way that you'd expect, but only if you expect it.
Well, it's actually there's a very simple explanation for comets. They're giant tektites. That's it. They're just really big tektites, which means they're hollow inside, which is why they're so light compared to their size. They're just hollow. How hard is that to understand? They're hollow. They're hollow, and they're made mostly of metallic materials, and they're on a very extreme elliptical orbit. If they're traveling through the sun's electrical field, EU theory aside, if such an object is traveling through the sun's electrical field, it will do this. So it completely destroys. But the problem is, if you accept that, then you have to dismiss the nebular hypothesis for the origin of the solar system and of all solar systems.
And if you dismiss the nebular hypothesis, then lambda CDM and general relativity, by extension, has to go.
Yeah.
Well, they were good enough for a while.
Well, as was everything.
As was the Newtonian equations. Yeah, they were good enough for a long time. I mean, Newton got us to Einstein, and Einstein got us to here, so where do we go from here?
Einstein didn't get us to here. General relativity and lambda CDM is now holding back our...
Now it is. Yeah, but it was a stepping stone. It was just one more step, and people sometimes want to stay on that step, and that's their problem if they want to stay there. But it is a necessary step, and it does actually answer a lot of questions. It just doesn't answer all of them, and it doesn't answer any of them completely accurately. But hey, it's pretty good.
I think. Well, special relativity is pretty good. I don't like general relativity, but anyway, the thing it threw away, which he snuck back in with space-time, was the idea that there might be a universal medium through which everything moves. That was originally it was called the ether, right? But
You can't say the A word. That's a Birkeland word.
it was supposedly disproved by the Michelson-Morley experiment.
Until it wasn't
Um,
proved by the Michelson-Morley experiment later on when they reconducted it years later correctly.
Right.
That's
Right,
correct.
yeah.
And Hiller did it as well, and he got a positive result. But by that time, the establishment was just calling them names and telling them that they're just was sour grapes and all this, and they were ignored.
Yep, they made a mistake first, and that mistake followed them for the rest of their careers.
Yeah, and I believe the tests that were done to actually initially test for that were trying to basically test for like the concept of like a static ether, where we were essentially passing through it in space, where like you could have the ether very much being like dragged with like larger bodies, and that's quite possible as well. And that's some evidence was found for that, I believe, in some of the other tests that were done. So
Yeah, when they did the tests at different altitudes, they found a variance. So that's how they did it. They did it at different altitudes, and they found a variance. And like, oh wait, there's actually a variance. It's measurable. And all that happened was the establishment nitpicked everything about their experiment and wouldn't listen to them. And they insisted that no, they had not made the mistakes that people said they made, but nobody believed them. Right.
And nobody else wanted to do it after that, because nobody wants to go through that shit like for their career.
No.
And then by the time all of it was forgotten by their peers, well, all of it had been the other way had been accepted, and then all of a sudden people think it's the way it is. Like lots of shit like that.
And I will point some fingers at the original experiment too, because those two brilliant minds with a good idea made a terrible mistake before they conducted the experiment, and that was to make claims that they were going to prove something. And that got everybody's interest watching before it was conducted. So naturally, when it didn't work, now they had to eat their own words. If they hadn't put their pride on the line there and had to make a claim before they had the results, then there would have never been a problem.
Mm-hmm.
Right. So there is some blame that they have to take for ruining their own careers in doing that.
Sure, but I'm just what I'm implying is, so we were talking about radical models. So let's assume that whatever the quantum zero point is actually some kind of universal medium through which on which the entire universe is scaffolded, and that universal medium isn't it's semi-dynamic, meaning it's ubiquitous but perturbable.
Yeah, the universal medium is kind of a strange concept, but it's sort of like you have a bunch of kids playing in the playground, and every time one more kid walks onto the playground, it gets slightly bigger. That's the sort of dynamic nature. How do you make a measure if you're the person going in to measure how big it is? Because when you leave, it's going to get smaller again, and that's particles entering their energy and changing the dynamic space.
What if they're not really particles? What if really the definitions of these points is just by their connections, right? So each point could be like complete, has absolutely no dimension, but its qualities are defined by the number of connections that are coming in and out of it. And then as the quality or the polarity of those connections changes, if you will, that the information still flows through the connections, even though there's no point there.
And I would agree with that too. So you get this emergence of something called space as a result of these point connections that do not have the property of space.
Right. Yeah, that's what I'm trying to model right now. Basically, that's my
model.
Well, what if everything is fields all the way down? And what if this universe?
Yeah.
What if this universal medium? Well, that's a good question. A field is something that is defined by its area of effect, not nothing else. So. What I'm saying is, what if the idea of particles is a convenient model to a certain level of precision that we use to apprehend what is actually simply blobs of, we'll call it energy, whatever the hell that is.
Mm-hmm. Information.
From what we've been able to measure, that's definitely the case. I mean, the size of a proton, for example, is something that's been a tremendous difficulty to measure, and
Yep.
The general explanation for it is, well, we just can't measure something that small because the tools that we're using to measure it are made of the same things that we're trying to measure. But that's not really a good explanation because we found our way around that. The real reason is the size of the proton doesn't have a size on its own in the absence of all other protons, electrons, and neutrons. It requires those things to exist in order to have a physical size, and it's defined by its interaction with all of those other things.
Right. So I have some there's a place, and the reason we're talking about all this again is because of like cellular automata and all of this. It is in my experiments with cellular automata, and I'm sure I don't know if you guys have ever played with them. There are lots of cases where the rule sets and some starting conditions will generate these structures that are essentially that are stable and that move through the space of the cellular automata. And to me, right there, that tells me this is something to look at in terms of like potential like way that like going back to this doubly connected grid. Again, if you have a set of rules with how this grid responds to its neighbors, right? Every point is the same, and it just has the same rules. It's connected to like points around it. And it just responds in a certain way based upon how information comes in. So like, and then it just passes that information along. That's all it does. Like, and if just from that connected grid, if you perturb the connections in a certain place, you're going to cause a ripple effect that's going to go out, and that ripple effect based upon how like those initial conditions start and evolve over time, if they form structures they can form structures that are stable and then that move through that environment. So to me, that points to this is probably like, a good place to look in terms of like trying to model something like that, or at least get close to it in a way that kind of sort of looks like it might be, similar to the way things work.
If we can find a way to model fundamental quote-unquote particles as dependent field phenomena.
Yeah. I'm going to step away for just a few minutes. I'll be right back.
Huh?
Then you generate the possibility of creating an emergent diagram of how they might behave. Because, of course, emergence requires dependence. It's dependent on its environment.
Right.
So, but a particle, the way we handle particles generally, except in quantum theory, but is as a sort of unitary thing. So you have a proton.
Yeah.
It has a certain charge. It has a certain mass. It has all these behaviors.
Right.
But what if it's actually what we've observed is just the average, like that the dead average behavior of all protons, generally speaking.
Sure.
And,
or is it just a structure that's stable at that particular size because of the very quality of space of whatever this stuff is that we're all made of. Like that's the way it comes together, and that's the geometric like sweet spot, right?
Then there's movement without movement.
Right.
Which is essentially positing that, to put it in layman's terms, everything might be hard light or a pseudo form of it.
In other words, if you think about if there's a medium, and all particles are field phenomena.
Yeah.
And the medium, you can imagine the medium as something like a, pseudo infinite, some incredibly dense field of pseudo particles that are vanishingly small and have no particular characteristics. Then the field movement, kinetic movement, would simply be the field phenomenon's biased travel through the field through the medium. In other words, if you imagine soap bubbles, you imagine a bunch of little this is a really crude way of looking at it, but if you imagine a bunch of tiny little particles that you can barely see in a big soap bubble next to them, and instead of moving, what happens is the soap bubble distends, and once its distension touches the next particle in a certain way, it suddenly it transfers over to where that part of the medium is. And if you say that there's some asymptotic limit. So like there's some huge number of these quote unquote medium particles. Then you'd have smooth motion. It would be undetectable as quantized motion. So in other words, it could be that all motion is in fact quantum tunneling.
Yeah.
Yeah.
Which
is on
the
such
case
a small
means-
scale, that we don't notice that it's not. There's no that it's happening.
You wouldn't notice anything until you take a measurement anyway. So, and then your measurement's only good as how the space is constructed to make that measurement, which is kind of like how it's an interesting reinterpretation of the Heisenberg uncertainty principle.
Mm-hmm.
Well, and if all motion is quantum tunneling, which we don't know if it is or not, but if it is, then what that means is we might be able to exploit that to essentially create the infinite improbability drive from the Hitchhiker's Guide to the Galaxy.
Right.
Essentially, you could, if all motion is quantum tunneling, then what's to stop you from quantum tunneling an entire object across light years?
Mm-hmm.
Yeah.
It may not require lots of energy. It may just be it may simply be
according
how
to
you bought. Yeah, go ahead.
Yeah, according to the causal graphs, it's just about creating a bifurcation or a branch, in the causal graph of how all the interconnected space. It's the same way you create a quantum computer. So.
Yeah, a Bell's apparatus is a much more simplified version of this, of course. Which doesn't actually, which does a slightly different thing. But you're not. That's so. Yeah, I mean, the reason Dr. Weird and I have talked about moving without moving before. Which is why I saw the smirk on his face when he brought it up.
I just stepped into somebody with a smirk on their face. What did I miss?
Yeah. So it's an interesting idea, and I think this is what I'm talking about in terms of going radical, like playing with radical ideas. This is just one of them. To try to figure something new. Try to figure out something new, because what seems to be happening is we're resting a lot of our posits, a lot of the posits we make upon some subset of the standard model, which we can't really avoid doing. But where we choose to make that stand, I think, is important, and how crazy the conjecture is. And if it fits in, and then if you look back at it and say, well, does this actually fit in with observation? Does it fit in with, could this also be true given what we know about how experiments have been conducted and have happened?
Yeah, I guess that pretty much means all of string theory is out.
Yeah, supersymmetry is nonsense. Oh my God. It's just like, it's just.
I know,
like,
it was low-hanging fruit to poke at it, but had to take a chance.
It's just, I'm sorry. And I hate Michio Kaku, by the way. And I bring him up because he's a string theorist. I hate him. I don't like him. I shouldn't say hate him. I dislike him.
I think he's a highly entertaining person who is wrong fundamentally on the nature of the universe. Just like Neil deGrasse Tyson is extremely entertaining.
Right. I think part of how you have to be popular and entertaining is to be wrong a lot of the time, because it's like you can't have someone who's right about everything, because it's much more popular to be wrong because it's easier to correct them, and I don't know. That's
Neil deGrasse Tyson got famous is because of the way he would get into an almost outburst like state, get really upset when his ideas were challenged on stage at debates. And of course, people are going to want to see more of that guy doing that stuff. So
yeah, I mean, he's had his ass handed to him a few times, and he does not.
So many times.
He doesn't like it, and it's like, dude, are you? This is. Oh yeah, I wanted to bring this up. That this only proves. This basically proves that he is not a scientist. Because I hate it when people say, "Are you a scientist?" and the person says yes, and then they come up with some kind of, then they behave like Neil deGrasse Tyson. It's like, dude, there are two. You had one job. You had one job, man. You keep two things in mind. All knowledge is provisional, and experiment is king. Those two things should be guiding your every waking thought. No.
Yeah, absolutely. That's why Feynman was so dead nuts on with all that stuff.
Well, Feynman was devastating, man.
Yeah.
I mean, people, he would admit he was wrong when he was wrong instantly. But
Absolutely, that's what made him so admirable.
Yeah.
But
Yeah.
then he would just, when people were trying to give him emotional arguments, he would just ruin them.
Good.
Wanted to see if you guys were interested
Yeah,
in
Bill
looking
Nye.
at what interested in looking at the thing I'm modeling here, in terms of how I'm putting this grid together and how I'm like deriving the grid from basically nothing.
Can you do a screen share?
I don't know if Skype can do a screen share if it can.
Yeah, it can.
can.
There's a double. There's like a double window, a double box window. That's
Okay.
your screen share.
Can you see my screen now?
Yes, we can.
Yep.
Cool. All right. So basically, I'm just playing around with this really simple equation that takes that takes a couple of node connections, and what's this? Okay.
Sorry, I just.
That takes a couple of node connections that are basically zeros, and then iterates those zeros with essentially adding another. So what's happening here is I'm taking two zeros, and then I'm joining itself with a new particle that's connected to the initial 0 point, right? So it's the zero itself splits off into two nodes and then keeps on subdividing, right? So I've got essentially what starts as a zero, which is two double connections, and from there, this thing is mirrored further on here, but essentially doubles here, and then every generation, as it doubles, the 0 point is maintained as a connection with all of these other nodes that are related to it, and then after a few generations, it forms essentially what could be used as a three-dimensional interconnected grid structure where as you get to a certain point, this thing is not just evolved maybe it evolves until it's stable enough to connect with itself in its own reflection, right? So like imagine maybe this thing evolving in like a mirrored cube. As it evolves, as it like more and more points appear in its reflections, it's not going to be like a stable structure. So it's not going to be like lines out into space. It's going to be like broken lines because it can't. You guys know what I mean? But you get to this certain point where all of a sudden it is stable. So like here you've got up down. You've got basically the three dimensions as a grid, and at that point, that structure is stable, and those reflections are stable as well. Maybe that's how it. Maybe that's why three-dimensional space is stable, because the first structure that is similarly reflective, when you do this kind of a simple additive process that revolves around this not center, like the 0 point, at this point it becomes stable, and that's what reality is, right? That's what space is ultimately. I don't know. That's what I see when I look at this stuff. To me, this is the right direction because, well, I mean, I don't know. Maybe I'm just I just get too much into it, but it seems to very much match the philosophy that I see everywhere and that I've studied for so long in terms of things that everything is kind of a self-similar reflection of itself, philosophies say that all of reality is a refracted manifestation of the one reality, of the one that there is only one event, only one occurrence, only one thing happening, And even though there's only one thing happening, we see it from a refracted perspective, and from that perspective, there's all this multitude of refractions that have apparent reality and do have reality from our perspective, very much so. But at the end of the day, they're, maybe we're all just like a bunch of higher dimensional light bouncing around in like the structure that like has all these reflections. That's how I see the universe.
I think we all have to kind of go through a stage where we consider the one and this nature of the universe. In my quest, the only one I've found so far is the ether, but that's of course not the one.
Think of it as a mathematical concept. Don't even like put like any kind of like mythical anything into it. Just to take all that out of consideration and take the philosophical concept of the one, if you will, like of one thing, of one like or of like nothing, of like what Jeremy was talking about earlier, this concept of like emptiness. Like, is it empty, or is it like, or is it out of emptiness came everything? So is it really?
That's a lot of words to literally just say the word universe.
I mean, the problem you get into when you start trying to define space is that ultimately you end up in a double bind, because you're essentially referencing something from within. It's sort of like a fish not knowing that it's wet, if that makes sense.
Well, you know how I would define space? The way I liked the way Ken defined space when I was talking to him, he said if it's built out of these structures, then the way you define distance or space is by counting structures.
Well, yeah, but that's still not. What I'm saying is when you're using mathematics, what you're using is a very precise language for describing values and the interactions of those values and structures on each other. And to the extent that we've developed that language, we're able to describe many very beautiful and complex things, such as this really interesting diagram, and this interesting evolutionary diagram. But if you take one step backwards, there's a self. You were just saying it. Everything is self-reflective, and that's exactly what stops us from genuinely. Essentially, I've taught meditation to a lot of people, and they always ask me, "What is meditation?" And there isn't really an answer for that. I can just now. There's an answer that I can say a bunch of words at you, and then when you try a few things that I've suggested, you'll have an experience that I can tell, because I've accidentally tripped over the same experience that you're probably having. And then we can agree, oh, that's okay, now I know what that is. But there's no, I'm just labeling that experience meditation. And the problem is there's no way to actually point to it as a thing. You can only ever point away from all the things that aren't it.
Right.
Because there's stillness, there's contemplation, there's all these other things that aren't meditation. Yeah. Meditation is something else, and I can't actually describe
that analogy is probably the best one so far that really makes sense about this idea that all things in space have to be compared to this idea of not space or nothing.
Well,
right.
That's when you create duality, right? And like
correct.
And
the fundamental thing.
We're either creating it or we're inhabiting it. We don't know which, and that's the problem. That's fundamentally.
I really don't see how it couldn't be both.
What's senior here, like, is what's really being reflected. Is it maybe consciousness? It's actually the senior principle. Maybe it is the higher dimensional light that is being reflected. I mean, it seems to me that the nature of reality as we're able to measure it is certainly pointing to that. Therefore, it may be worth looking to see if that which is causing, or maybe that which seems to be so coincidentally associated with all this, may not be just the thing that is bouncing around and doing the illuminating. I don't know. That's the conclusion I come to when I.
In my no, it's a perfectly reasonable path to go down. In my case, I prefer to just take spaces as a given, because I know how difficult it is to go after it, and instead focus on soluble problems. And it's not like and that's not a criticism. This is really interesting work. So I'm not criticizing your work, and it's important. Just like how Boolean algebra was important, but nobody knew it until the computer was invented, right? But my point is that what we were talking about originally was we were talking about all these big giant balls and chains that are placed on people in terms of scientific research, and the standard models that we're using to apprehend everything. Almost zero people are genuinely being given the resources and the time, and all you'd really have to do is pay somebody to be a crazy motherfucker, who is smart and somewhat grounded, right? And just pay somebody to be crazy for like 20 years, go off on all these different tangents, and they might find something for you. But nobody's doing that, unfortunately. And what's like literally no one. And the entire
of course,
system.
the better solution to that isn't to have to pay somebody to be crazy, but just simply to fix the fundamental problem of people holding on to ideas that don't work in certain situations, and just admit they're good enough for the things they're using them for, but they don't work everywhere, and accept that.
I mean, so what APOC is getting at is that the era of the 40s through the 60s, where we basically paid researchers and scientists to make cool shit because it's cool, is over, which is why people like me have to go the route of self-employment. There's no way I can hold a job given the things that I do.
Yeah, same here.
I mean, I took a tentative dip in that, and I'm probably older than all you guys. And I took a dip
I'm
in
only,
that.
in the 30s, so probably.
I'm over 50, so.
Right behind you.
Woohoo! Oh, good. I'm not the nosebleed territory with everyone. That's nice. And so when I went to college for physics and mathematics and did all that, and at some point I realized that getting into it professionally was a bad idea, because I probably would knife some motherfucker in the face. Because I was so, and I'm exaggerating, but I mean, I was so frustrated with the insane bullshit. And this was back in the mid to late 80s, right? Early 90s. I just got so frustrated. I just walked away from it and went into technology instead. Because I was like, and what's really frustrating about it is I was working for a particular professor for a while, and I brought up a few things, I questioned a few things. I wasn't given the time of day. I was basically told to shut up and calculate or do my work or whatever. But I mean, the things that I questioned about what he was doing, he was designing a piece of equipment, and I noticed something about it, and I pointed it out, and he told me I was wrong for a bunch of reasons, and like, whatever, okay, fine, I'll just design the part. And I designed the part per his specifications, and he built the thing, and oh, wouldn't you know it, it fucked up just like how I said it was. But instead of saying to me, you know what, you were right. You were right. I should have listened to you. No. Nope. He blamed it on me.
Oh, man.
And laid me off. And he
That's fucked up.
I was so angry. I took it up with the ombudsman, and it went all the way to the dean, and the whole thing got stricken. But
What a piece of garbage.
I know, and this was at a very good university, FYI. So, this wasn't at
It's good that you
Just
get to
don't
see
tell me
that
it
in
was at
action.
MIT, okay?
I think it was
'cause
supposed to happen for a reason, though. I think these things happen to certain people in their careers just so that we're enlightened to the bullshit, that of the whole facade of it all, because otherwise it's hard to see through it,
It
And the
is,
strangest
and
part is we end up in places like this on this channel.
Well, I've had arguments with people about. I had trouble. I learned general relativity, obviously, and got into that a bit. And it's fascinating mathematics. So I was interested, and I learned what I could about it. And I started seeing some things that I thought were problems. Yeah, I started seeing things I thought were problems, like, why are you, what's up with the Ricci tensor here, and how come you're superposing this way, and I asked some fundamental questions about relativity, and asked how it was, what were the justifications behind doing these things, which, as far as I could tell from straight up normal differential geometry, weren't they weren't reflective of any underlying reality. They were just math.
But see, that's a feature. It's a
and
feature.
I said that. I said, well, this is not like you're superposing. It's basically, there's some things that are going on in the long form that didn't make sense to me, and I asked about them, and I was given an explanation, and I said, yeah, but that doesn't. Okay, but you're making but now you're making more assumptions that are not provable. Like but I was, oh well, there's, that's. But it works, and GPS satellites work, and It's like, yeah, but Einstein said they wouldn't work, which the guy I was talking to didn't know.
I didn't know
that. Einstein's, yeah, he said GPS satellites couldn't work because of the time dilation, because they'd be moving around the Earth so fast, and the signals. If you think about raw general relativity, that makes sense, because you're going to get the waveforms are going to be shifted in the wrong direction one way, and another direction the other way, and they're not going to be moving constant relative to each other. So how do you account for that without some other medium? And while your detection device is going to also be dependent on these same shifted wavelengths, and so he said he didn't think it would work. But
I guess I can understand why, though. I mean, technologically speaking, at his time, the necessary calculations and equipment to compensate for the dilation didn't exist.
No, he said no. He said the physics of the system he thought they couldn't work, no matter what the technology. And
right, but the funny thing is that his theory doesn't explicitly prevent them from working, so that sounds like a matter of his opinion of his mental application of that theory, because there's nothing in his theory that states it couldn't work. It sounds like he just had kind of made an assumption about what we could do based on that work.
No, he was. I mean, I see where you're going with this, but he was talking about, if you imagine a cluster of satellites remember, these satellites don't orbit synchronously. They orbit in clusters that move about, right? And that's intentional, so that you cover the most amount of ground with the least number of satellites, right? And you have to have a certain number of satellites available to make it fix, and all these other things, right? And this was proposed way back when, and what he said was that the fact that the time dilation was basically the time dilation that would occur as a result of relative motion between the satellites and the ground would be non-deterministic at any given moment, because of the separation between the satellites and the ground receivers and the satellites and each other. In other words, they wouldn't be able to get the precision that they wanted, and it would float back and forth always. Essentially, it would bounce back and forth, and you would never get a precise measurement. Now we do get precise measurements.
He got that
We
idea.
do. Well, you have to think about it in terms of differential geometry. But we do get appropriate measurements. And GPS satellites, by the way, don't correct time dilation. All we know, this is what we know. We know that GPS satellites have a clock skew of a certain value at the altitude that they orbit. That's it. And that clock skew is compensated for. But what we don't know is why. And the amount of clock skew that happens wasn't predicted precisely by general relativity either. It's been back rationalized into theory. This is part of the epicycles I was talking about. But when
all this is stuff that I'm not familiar with, but I don't understand why it would need to be the case at all, because I'm not seeing a gap in our current understanding of GPS that we would need to add this other factor.
We're fine now, but we found out how to do it through experiment. And the behavior of the satellites in orbit was discovered through experiment. They just put a bunch of satellites up, tested, found out where the problems were, fixed them. That data went back to the physicists. They changed the theory and the explanations to fit it.
So are you saying that it was basically found through trial and error? It was not we're not using a calculation of known mathematics or known physics in order to compensate the clocks. We're just literally compensating them based on what we found to work best. Is that what you're trying to say?
We're compensating them based on the value of skew we discovered they had at the orbit we were orbiting them at.
So you're saying that we weren't able to actually predict accurately how much skew they would need.
No.
We had to find it through trial.
No, and in fact, Einstein was talking about how the skew would be variable and so on between clocks, and so this is what I mean. Like now, it's quote unquote common knowledge that we do relativistic adjustments of GPS satellites, but it's not really relativistic. I mean, we don't know that it's relativistic. All we know is that the clocks are skewed when they're up a certain level. We only know the clocks are skewed. We don't know if it's actually relativistic. Like there's no other, except with atomic clocks, there's no other way to measure that we have, whether or not it's a universal phenomena or just a clock phenomenon. See what I'm saying? So I mean, measuring time.
To look into, yeah.
Yeah, measuring time and time are two different. A clock is different than time. So, we assume that clocks function based on and this goes back to our original discussion. We assume that clocks function based on a continual source of entropy over what we call time, and that those can be calibrated, and so we have a measurement for time and all this stuff. But the clock still isn't time. The clock is just functioning thermodynamically in a way we think is predictable to give us a time slice, a slice of quote unquote time. But we don't know that. Anyway, I know this is all very, very, very nosebleed territory, but basically, these are if you're going to get into rudimentary physics, like, I don't mean rudimentary, I meant, if you're going to dig all the way down, if you can dig all the way down to the turtles, right? Then you have to start thinking about things in terms of what are we actually measuring? What are we actually doing precisely?
Right.
And like in the case of black holes, we're measuring X-ray, gamma ray, and synchrotron radiation outbursts from distant objects and assuming they're black holes, because that's the only structure we know of with a gravity model that can generate outbursts of that magnitude in space. But nature likes to do things simple. So the plasma cosmology explanation for X-ray bursts in space is, how come you don't just assume that a bunch of electrons are being moved through an electric field? Because that's how we do it in a dentist's office.
I was thinking the exact same thing.
Right? It doesn't take much energy either.
No, I'm going to grab a water. 30 seconds.
I'm about ready to grab a beer. It's getting to be about that time. It's almost midnight here, and
So as we I don't want to get like, and all of that was just to say, as we look at these interesting diagrams, as you guys think about these subjects, I would suggest that you start looking at what do we know and why do we know? Why do we think we know it? And backtracking that to the original source. And once you get to the original source, you may discover something really interesting. Like Hubble didn't think that redshift had anything to do with recessional velocity.
Right.
In fact, yes, Zawicki's tyrant light theory provides an alternative explanation for the, as an alternative to the Doppler effect for the redshifting of cosmic background radiation. So indeed,
there's also
That's been a
Halton
huge
Van
point of
Arp's
contention for me
intrinsic.
too. Redshift.
Yeah, there's also Halton Arp's intrinsic redshift theory, where he thinks that, and this has been proved in a lab, in a plasma physics lab, that plasma discharges can have intrinsic redshift under certain conditions.
Yeah,
red or blue shift, actually, red or blue.
Interesting stuff.
Yeah, so I suggest that, and it sounds like the conversation's winding down.
Yeah.
I would suggest that you think about these things. If I can make a contribution as opposed to the specific things I was talking about, the general principle of when you're going after something this essential, you need to go way back into the assumptions that were used to create the original.
Basically, all assumptions away here, and understand that like the perspectives and points of view that each of all of the people that discovered all this stuff, and then the people that then started believing it, were all influenced by whatever they were doing at that point. And it was, like the people can very easily start to, believe something that, even though it provides a description that is accurate, isn't really not. It's just a model. Like all of it is just a model, anyways. Even our senses give us a model of what's happening.
Everything is a model.
That isn't real time. Like our own senses show us what is happening in the very, very near past, because it takes time for those signals to get to our brain. It takes time for our brains to perceive it. So really, anything that we perceive that has any kind of sensorial quality or quality of having been perceived is really not real time. There's something there in real time. Yes, I know there is, but it's not our senses, and it's not what we see or think about, actually, because if we think with our brains, then it's definitely not what we think.
Yeah.
Well,
Yeah,
I
everything
say
is a
we
model.
play make believe that it's 1855 and throw shit at the wall and see what sticks.
Yeah. That's pretty much what someone said. What are you doing with this Wolfram thing anyway? We're pretty much throwing shit against the wall to see if something sticks.
Yeah, no, that's 100%. And honestly,
as long as we can be honest with ourselves and not,
Real science right there. That's how it works.
Educated flinging, like there's enough.
Yeah,
evidence.
well, that's what we're doing. We're trying to come up with some kind of direction and science to the shit slinging, so we can be like, all right, well, if we throw it at a trajectory of this vector, and
We know our target. The only problem is the target is shrouded in darkness and shadow, so we can't really see exactly where we're aiming.
Yeah.
But we know that it's in that box of shadow somewhere. It's in there.
Right?
And if we hear something go, I guess we know we got it.
Well, I think that the ancients knew all of this. I think they had to have known something to build the stuff that they did, and so and I'm pretty convinced that it's not like whatever it is, whatever the missing piece is, whatever the model is that we're looking for, isn't going to be so radically difficult to understand that it will boggle the mind just to its implications might be radical, but I think it's not going to be necessarily all of that crazy, and I think it will be elegant too. I think I don't know who was saying that things tend to the simplest, kind of the lowest energy state.
Occam's razor.
Usually the most balanced state is where the universe, where symmetry seeks to be at. It's just a fundamental property of everything. And so, you have to, in any situation, I tried to look for, what's Occam's razor in terms of explaining some bullshit I see, or what's likely to govern a physical system, and what are the laws that, what's the simplest method I can come up with that achieving that effect, and kind of look there because it's likely that I'll probably find something interesting.
Right, yeah, I agree with the elegance idea too. That's one of the phrases in engineering is your job as an engineer isn't done when you've added all the features. It's done when you've taken away everything else that's not necessary.
Yeah.
Oh,
And
don't
always
tell that to
remember
GM and Ford.
Speaking of technology and stuff, we have, so I should bring this back to the anti-gravity group that many of us are part of, and in that I just recently posted, I have successfully built and tested an ultra-lightweight power supply weighing in at only 11 grams. It can produce 88,000 volts, and I was able to achieve 40 watts out of the thing, which is just insane.
It's insane.
I wish I brought the pictures up of this. I wish I.
That's impressive.
You were
Yeah, I don't know how you soldered anything that small, man. That thing was tiny. I don't know.
It's like this. The whole entire driver circuit and transformer is just slightly larger than my fingernail. So
it's unbelievable. And like
Congratulations.
How do you sync the
how
heat?
to do some serious lifting on a.
It's so small that it sort of wicks away its own heat. It turns out that you get pretty high thermal transfer on small surfaces like that.
Wow.
Yeah, the MOSFETs are only 0.5 millimeter thick, dude. Everything is super duper light. The two MOSFETs together only weigh 0.01 or 0.166 grams. So that kind of gives you an idea of like how small and lightweight these components are.
That's unbelievable. Like
0.007 grams for my control circuitry. And
I am actually pretty shocked about how much power. Here, I'm gonna turn the video off, but I'm gonna show the video.
Yeah, we can't see the video though, Jeremy. I don't think. Oh, maybe we can. I guess my video is lagging behind on YouTube.
Almost 30 watts.
I just want to show a picture of it.
I want to see. This is. Start building some flying shit with this. Holy crap.
That's exactly what it's for. It's supposed to lift its own weight, battery pack, and acceleration grid, so it should contain everything.
That's the size of the thing.
Wow.
Let's see it.
That's incredible.
So, pretty
It's
cool.
taken a long
We're
time to get
building
to that
stuff.
point.
I call it our gravity research lab, but anti-gravity, it works both ways, I guess. We're just trying to figure out what gravity is and test it and try to find ask the universe the right questions to try to get the right answers is kind of, the name of the game at this point.
If you're curious about alternative theories of gravity, let me throw a link in the chat. Actually, it'd be easier.
Okay.
There's an EU theory of gravity, which is really interesting. If you guys are curious.
Who's it by? Verlinde? Van Ramstok?
No, Wal Thornhill.
Wal Thornhill.
Oh, I've heard of him. Yeah.
This guy.
Okay,
More electric universe theory.
It's interesting.
Where did you talk? Did you put it in?
I'm
chat?
putting it in chat right now.
Okay.
Yeah.
It's an old link, but it's an essential primer. There are newer models, but this is essentially the model they're going with. They're still playing around with it.
All right, I'll post it in the live chat just so people can check it out. Again, I haven't looked at this or spent enough time with it to really have an opinion on it.
So
that's my thing that I'd like to emphasize is that, for anyone studying, trying to actually make the technology, trying to create new mathematics, to do that requires good models, and we don't have good models. Yeah. We have decent models that have their own issues. So if we're actually looking to make physical technology that's useful, to heck with the textbooks. Just throw shit at the wall and see what works.
That's kind of what
that's what Maxwell did. That's how he developed he developed all of his equations from experiment.
Yeah. I'm just just playing around with this stuff. I like to play around with systems that start out with simple rules and blow up to amazing complexity and show all kinds of interesting emergent behavior, because I can learn a lot about how natural systems work just looking at that. Or I can just have fun and just trip out. There's something there's something really interesting about kind of exploring the computational complexity of simplicity, and to me, there's something there to find, because I've already seen from simple things I've played around with, some pretty profound things. Now, I could be just out of my mind. There's a very real possibility of that. In fact, that's likely the case. But in case I'm not out of my mind, I think that it's something that I've been driven to look at my entire life. And so, and all of these things keep connecting, and my insight keeps taking me to places that keep confirming it. And so that must not be, there must be something here. And we're all going through kind of the same thing. We're all approaching it from different angles, maybe a little bit, or have different backgrounds or whatever. But all of us know for a fact that the current dogma is not it. It's not it. And that's good enough for me,
Yeah,
That's
there's
why I
good.
think
There's good
that's
and
why I
bad
agree.
data.
That's why I agree that what needs to happen to change things is experimentation, and as was said, literally throwing shit against the wall. And the experiments don't have to be expensive; they just have to be done in ways that wouldn't normally be done, and to see if there's a replicable effect.
Yeah, and if that doesn't work, there's always brute force trial and error.
Yeah, absolutely.
I had to select through my over 100,000 components to choose the exact 20 components that I would use for that power supply, and that came from over 15 years of collecting parts. So it ends up, it's all building on itself kind of thing. But you start out with simple ideas, and they become much more.
That's
I
awesome.
once had to
What are you going to
search.
use it for? Are you going to make something that flies with it?
Yeah, it's going on a little. That's one of 4 identical power supplies that needs to be built for a ion-powered quad drone.
Oh my God, I can't. You have no idea how excited that just made me. How quiet will that be when it flies? How much noise?
You can't hear it from 10 feet away.
Oh Lord, that's terrible. Oh my God,
it's terrifying. I'm equally
I'm terrified
of
right now.
And
We have to
I think
Do
we.
not
I
be
think we should be.
terrified of the future. Embrace it,
yes.
because decentralized manufacturing, decentralized energy, decentralized currency, decentralized communications, and
I'll tell you
decentralized food production will truly liberate the individuals and make it virtually impossible for anyone to control or enslave anyone else.
If you survive the swarms of decentralized hunter-killer drones that are going to be let loose by terrorists that are just going to fly around and kill people. So I'm going to get myself a personal protection net of whatever kind there is out there when drone warfare hits the scene, because once that happens, that's as revolutionary as firearms and freaking swords were. Because once you have a silent drone that can carry an explosive payload really fast, people are fucked.
Yeah, facial recognition. What was that video? Slaughter bots. You seen that?
I love that video.
Slaughter bots. All right, we'll end. We gotta watch this for the end. This was crazy. The slaughter bots.
Oh yeah, that terrified me.
Yep, that's definitely. If you want to have nightmares tonight, watch this before you go to bed. And
it's the most realistic horror that I've seen in a super long time.
This is pretty crazy, and it's got a little charge in it that can blow your brains out, and the facial recognition software, so it just sees you and knows who you are, and it will just fly right into your forehead and blow your brain out.
I would like to say, it's a good thing that this was just a short movie put together by somebody as a pet project, but you know damn well that if somebody thought of this, it's already out there.
Right.
Oh, for a fact, there's several teams working on them right now.
Yep.
Guaranteed.
And that means that there are already several models that are out working and deployed right now.
Yes.
Well, see, but the good thing is with drones is we can take like a dozen of them and reprogram them to, instead of explode, to spray paint, and we can correct the horrendous mistake of making the bronze bull in New York in front of the stock exchange, and we fill it with a gold flake yellow based paint. We can finally correct the color of their idol.
Oh, there you go. There
That
you go.
would be
Well,
hilarious.
don't worry about their idol. They'll be taken care of soon as mathematics and like reality catches up, and the whole thing collapses into a heap of over leveraged and overvalued garbage that it is. So because it's like it's bound to happen. Again, it's a just like this. Well, I don't know whether like hopefully everybody on this channel believes in the virus because it's real. But exponential functions are a thing. So like humans, we should, when we see a virus somewhere else start to spread really quickly somewhere, do something about it immediately. But we don't. Why? Because we don't have an intuitive feeling sense for exponential growth. And by the time it catches up to us, by the time we notice it, that function is like one iteration away from blowing up, past 100%. So it's like we don't ever see it happening because we don't notice until it's far too late, right? And so like a lot of these kinds of and like you were talking about transitions between curves too, Jeremy, where like you have like two systems that are kind of defined by like two curve transitions, and at their junctures there's a sharp transition between like two states. That's kind of how nature seems to work in a lot of cases. Like zones of equilibrium are defined by kind of they're places of stability that then very quickly change into chaotic zones like when their bounds are crossed. I'm just mumbling about stuff that's coming to my mind here. But that kind of stuff is very much like a fractal too. Like a fractal has this quality, right? Where like the function either blows up into infinity or is stable in a particular zone. So chances are reality is just like that too. It's a fractal, or at least the kind of distribution of stuff in it should be fractal in some whether in size or something like that, I don't know, but one would think.
I suppose the point of the matter that I have to emphasize here is that if anyone wants to actually start researching and developing this technology, they're going to have to follow it like Maxwell did. They're not going to be able to model everything out nice and perfect and all on the chalkboard. You have to take that piece of chalk and they're going to have to throw it out the window and just start building.
Yeah.
The chalk is useful for only one thing: recording the results of the experiments.
Yeah. You'll have to start making guesses and experimenting and seeing what happens, which is what he did. He did bidding from observation.
Yep.
Yeah. Has anyone done any work on
he took Ampere's law, Faraday's law, and kind of just was like, all right, well, these are generalizations, things we know, and how can we come up with a more, unifying theory that unites them all under one single kind of.
So we all know about like T. Townsend Brown, obviously. Like he's like one of the big ones here, right? Like his research was interesting to me because it kind of led me down a few rabbit holes years ago, and led me to a place where I was seeing these diagrams for essentially capacitors that were built intentionally in a very asymmetrical way, either relative to the surfaces of the surfaces of the capacitor, or in regards to the dielectric itself, so that the dielectric could actually be biased. The K value of the dielectric could be like built in such a way as to have the electrical field be asymmetrical, and that potentially produce electrogravitic effects. And I actually did an experiment years ago that was really like, and I'm not going to make no claims at all, but it was like totally off the cuff. And I basically built one that was built out of titanium dioxide as one of the capacitors. One of the dielectrics, and I used one type of plastic, I can't remember, as the other.
Okay, let me just, as you're going through this, because this is an experiment that I'm also doing again, here, and I'm
Yeah.
using titanium dioxide as a dielectric in powder
Yeah.
form, mixing it with epoxy. So,
Very
sort
high-
of spell out what you did exactly with this experiment and how you mixed in your titanium dioxide, or if it was a solid piece. Tell me a little bit about it. What was your process?
What I did is basically I bought some titanium dioxide powder off of eBay at the time, and I mixed it in with some kind of, like, I don't remember what type of paint, I don't remember what kind of stuff it was, a lacquer of some kind, and got that stuff as thick as I could, and basically that's what I did. It was, like I said, completely non-scientific. I had some one day, and I had the materials finally, and I was like, I guess I'm trying to do this. And I put the whole thing together, and before it flamed out spectacularly after I had, put about 20,000 volts to it, it jumped enough to get me to thinking that something was going on in there that would work. I could just make something that had any kind of precision and geometry that made sense. That there was likely something there, biasing those electrical fields so that they're shaped in an asymmetric way. The theory that I saw behind it that kind of explained what there might be there is that the fact that, again, an atom is composed of positive and negative components. And so if you bias an atom in an electric field to kind of like stretch it out in a particular way so that it's aligned in a particular way, it will either generate the effects or just provide basically a medium in which the natural flow that's already there in all directions is biased to go in a particular direction. Which, so to me, kind of all of that sort of makes sense in different ways depending on what you believe. So that's one that to me showed a lot of promise. And another one I think might be fun to do is just do like a layered one of some kind, like I don't know, aluminum foil and some good thin like Krylon or whatever kind of dielectric. There's a million different stuff you can get out there, but I don't know. All of that just takes a lab and time, which is something I so desperately wish I had. As it is, my half my house is full of bits and pieces. So I don't have space for it.
Well, as long as they're organized, it's not a bad problem to have. Otherwise, it can be a bit much.
That's basically what I do. It's just like when I can't build stuff, I go through and just like organize it because it's the next best thing to actually building something with it.
I wish I had that habit.
My OCD.
My place is a crazy disaster. There's
There's
little
my
projects and pieces everywhere.
Like everything else of mine in my life is total chaos because I don't give a shit. It's just these particular things that I have. I'm obsessed to like keeping clean because it's I don't know why.
Like I said, it's not a bad problem to have.
Yeah, right. But yeah, there are a lot of ideas out there too. Like they're still out there on the internet. But like I remember reading this stuff way back in the day when there was the J.L. Nodin site. I don't know if you guys remember him. Then there was like American Anti-Gravity and like
I
all this
remember
stuff.
AAG, yeah.
Yeah, like back in here. But like JL Labs, I think it is. If you want.
You're talking about Jean-Louis Naudin.
Yeah, Naudin. That's it. Naudin would be how you say it in French. Sorry, I was born.
That
in French.
guy didn't, and it's hard not to give him credit because just how good he documented the stuff. And there was another thing that he did, and the reason why his site's still up, and I think why it's persisted, even though it's not changing much these days. He would produce results. He would show them in chart, but he would never give you the actual explanation of what they meant or why they were significant. He would leave that illusion to you.
Oh, I hated his guts for that, but at least he showed me that there was something there. I know his site is still there, and it's like it would drive me to madness that like I would see part of it, and I was like, but where are the fucking numbers? Like you're gonna give me this now? But what it actually did do is it did drive me to sit there and obsessively try to think through and like how would this work? How would this be like come together? And like so there were some things that were like fun to play with. Lifters, I had a great time playing with. Holy shit, that was fun. Like dangerous as hell, but
It's
fun.
not dangerous. Come on. It's only dangerous if your voltage multiplier has a huge amount of capacitance.
Yeah, I'm still trying to like get, like, I don't know.
That's why I like these little ones, man, because you can touch the output directly, and you'll feel the spark, and it'll hurt, but you're not going to get hurt from it. There's so little energy there. I mean, there are only 100 picofarad capacitors on that thing, so it's just like nothing.
Yeah.
And 8 of them in theories, you only end up with a total capacitance because you have two sides of 20 picofarads, which again is pretty small.
Yeah. So speaking of an engineering thing, maybe one of you guys like knows about this and can like help me find out about it again. So when I'm in my mid 40s now, and when I was 18 years old, this chick that I was dating fucking shows me this device that was like two freaking solid bowl hemispheres. Put together with looked like kind of tape in between it, and some dials and a place to put like a 9-volt battery. And you would turn the thing on, and you would hold it like each hemisphere in your hand, and you would feel like an electrical pulse, but it did not feel bad. Let's just say, this thing was like the closest thing to an electronic pure pleasure generator I have like ever seen.
I have no idea what that is. I want one, whatever it is.
Yeah, me too. Like, and I wish so badly. Like, if you are out there, whoever you are, I don't remember your name, girl, but that thing, I'm still obsessed with it. I still want it. Please, like. That it was amazing. It was like nothing I have ever seen, and I have never been able to find any information on it. But it was basically a thing that was like that produced apparently some voltage and some particular pulse shape or whatever it did that made it so magical that it was just like holding pleasure in your hands, basically.
Push button, receive bliss. That sounds like a nice solution.
Yeah, I mean, it did like eventually you would get like there would be a feeling of like, being kind of having enervated the whole like nervous system, so you couldn't like hold it forever. But I'm sure somebody out there would try, if given the opportunity, because it definitely.
Yeah, one of the strangest sounding devices I've heard of in a long time, and I have absolutely no idea what it could be. It sounds like nothing I've ever heard of.
Right, it's the strangest thing I've ever seen personally in terms of like devices I've held. I've seen weirder things, but I've held that in terms of holding that one takes the cake.
Yeah, that's an experience that'll stay with you.
Yeah.
Well, hopefully whoever that is does come back out of the woodwork someday, and you can figure out what in the world she had.
God, it's some kind of some type of like, some kind of magical, like the right frequency at the right voltage with just the right amount of power. To do it. I'm sure there's a right frequency that'll do the trick. I mean, I
don't even know if I go that far. It sounds like it's operating in some different way, because I've been exposed to just about every frequency you can imagine, electromagnetically and electrically directly, and I've never experienced one that I would call a pleasure frequency or anything, in fact, that felt any different. It was just all mild degrees of various being shocked.
Interesting. Yeah, this was the only time that really feeling of electricity through my body was like a pleasurable sensation. I mean, it was. Yeah.
If you think back and put yourself there, did it feel like a pulse? Was it something that was kind of did it tingle for a second, or was it like this kind of?
Oh no! Like let me tell you, I can put myself back there right now and feel it. It's still that. It's still, my body still remembers it that intensely. Like in fact, just thinking about it right now is stimulating my my pleasure, like my desires for it.
Let me go and ask another question. Did it make any kind of a sound?
I don't remember it making. Maybe I feel like it made a sound in my head.
I mean, that would make sense. You would be able to hear an electrical sound if there was one. If it was a pulse, you should be able to pick that up auditorily.
Yeah, there was something. There was like there was some kind of feeling. Like I don't remember right now. Like I can't tell you exactly, but I can. When I put myself there, there's a feeling like yes, there was some type of stimulation of the auditory sense, but
a buzz, a pressure, tingling? I mean, how would you describe it? Is it more like a buzz?
Combination of buzz and tingling. So like the kind of the wavefront of like buzz and tingling. Basically, it was just
That's
like
just a series of very fast, short, close together pulses.
Yeah, like it was very unique, and you know, like if I was inclined like to do an exploration, I would look at exactly that, like extremely short pulse types of waves. But the thing is like this. Remember, I was 18, so this was like again 92 or some shit. But yeah, 92. So like the technology in that thing was not going to be high tech. Like I remember
Yeah, but it
like
probably didn't need to be.
It's true. Like you just need to know how to put it together for sure.
Right. A basic timer oscillator, a high voltage amplifier, some simple components, and a power source. You know, that's pretty much all you need to operate a tens unit. So if it operated in a similar fashion, you shouldn't need much more.
Yeah, it's true. It's true. Well, if anybody out there hears about it, then you know, leave a message, because fuck, man, I'd do anything to find that again, and if not just to document it, mind you. It was off the hook, and it would make the thing is I don't understand why like it never saw it again, because you'd have to be like, I don't know, like you could make so much money with that thing.
Yeah,
you
right.
could
For
so
real.
much money with it. Oh my god, if I had one right now, like I could make $1 million in like less than like I don't know.
I know.
Less than a week.
Just sell it to Coachella or Burning Man too.
Fuck yeah.
Play the pressure frequency. Come on.
Fucking, I'd go straight to fucking.
Yeah, of course it would sell. I mean, think about how much the Hitachi Magic Wand has made.
Yeah.
I go straight to Elon Musk. You know, that fucker's got a ton of money, and
Hey, we could use this proceeds from our sex toys to fund our anti-gravity
weird
lab.
shit. Like, I don't understand why like multi-zillionaires like that don't fund this shit to the hill. Like if I had that kind of money, that I would just like fund like.
Well, sometimes they do.
Like,
You have Bigelow, that entire corporation. Bigelow goes on and talks about in an interview how he has not of this world technology that they've been backwards engineering, and he's a multi-billionaire. So yeah, it does happen.
That's cool. Well, that's cool. Then you should do an air show, because I want to see. I mean, like I don't want it just to know that it's there. I want to fucking see that it works. I want to see it flying around. So let's go. You know, like. I appreciate Bigelow for all the work that he's doing behind closed doors. However, the tours are closed.
I appreciate the fact that he's actually talked about this stuff not behind closed doors, and that he's actually kind of proud of it. You can see how proud of it that he is to have acquired that technology in the interview.
Oh, he is. He genuinely is, and I'm psyched for him. I really am. I would love to see an open source, you know, collaborative venture that comes together and like makes this science happen and makes it real, and just like brings it back to where it was, like it always was, like for a long time. Like science ceased to be the realm of the hobbyist when quantum physics just became a thing. And before that, you had folks like Darwin who started entire branches of science and who were amateurs, and like. There's a lot to be said for people that can think creatively, and honestly, you don't need to you do need to know like obviously what you're talking about, but you don't need to be to the nth degree in a field that you're already trying to bring something fundamentally new to. That's like ridiculous. Like you can't be expected to be like an expert in some field if you're coming at it from a radical perspective and you come up with something that works. Like
no, and you need both. You need the people that are going to be outliers, basically ignoring all the rules, policies, and theories to try just about anything that their minds can think of.
Right.
But in the same vein, in order for them to get to the point where that technology is made available, you need to work on fundamentals and have a good framework built up, a good foundation. So like I can do my research all I want and try to make really amazing tech, but I'm making that amazing tech out of other amazing technology like the power MOSFET, like the lithium-ion battery, like the miniaturized inductor, like the new ceramic capacitors with a K factor that's 200 times higher than Thomas Townsend Brown ever thought it was possible to achieve. And so it's like, I can only do what I do and try to do these crazy things way outside of the boundaries of current models of physics because I have access to these parts that were made from the boundaries within our understanding of physics. But at one point, way back in the past, all those things were started by somebody who also was just taking a stab at things and guessing and trying things out. So there is cycles of trial and error followed by cycles of good documentation and recording of the results so that you don't have to make the same errors again.
Yeah. Well, I love hearing shit like that. Like that just like have all these parts and you're like building this amazing stuff, because I really do believe that like that is possible. Like people that can have a clear model of what they want to do and just go for it and experiment, with what their intuition tells them, because like a lot of the time there's something really worth discovering if you're really pulled towards a particular place. And like everything you just talked about with all the capacitors and everything, the K value of how high of a K value are you like achieving with the dielectrics in your capacitors? And
well, I mean, me personally, I can't achieve any of it because it requires tremendous machinery and high-tech equipment to build these types of capacitors and compress them that hard. But now I think that these are 500,000 K.
Oh my God!
So
that's amazing.
That's what I'm saying, dude. That's why the entire multiplier and semiconductor diode assembly only weighs 6 grams.
Yeah. Wow.
And it's like, it's a pretty amazing feat. And that's with the dipping on the capacitors mostly still intact, with the diodes not having been shaven down, which is all things that I could do. I could actually turn that whole thing into a 3-gram multiplier if I really wanted to do the extra work of taking off all the insulation and then adding my own that was thinner and exactly tuned for the spacing.
Unreal, man. Oh my God. I definitely want, like, how can I keep in track of what you're doing? Are you publishing this stuff somewhere?
How are you keeping track? Get on the WhatsApp group, because that's basically where I'm posting updates.
Okay. Right on, right? I definitely will. Holy shit, that is amazing. Like, I have been following this stuff for years and looking for where is the innovation with this. And that's it right there. Because like once you've miniaturize it enough and gotten to enough of energy density and power level with these things, you can fly. You can build like flying machines, no problem.
This has been over 40 revisions now of various multipliers I built throughout my life, and this is basically the culmination of all of the things that I've learned about what is absolutely necessary. For example, this thing switches at 480,000 times a second in order to get the energy up through these tiny little capacitors. Just the concept of trying to switch something like this at 60 hertz, you would never even know that it was working. You couldn't even measure it.
Right.
But you bring the frequency up, and all of a sudden those capacitors start looking more like conductors to that AC wavefront, and then you can get the energy all the way up through the series chain.
That's right. Wow. That's really, really cool. That's really cool.
It's fun. It's. I know we want to do all this anti-gravity stuff, and anti-gravity is the ultimate goal, or should I say gravity control technologies are the ultimate goal. But in the meantime, one of the things that's going to get us there that we can do right now with current technology and with current theories is the ion propulsion stuff, and that's why I'm putting so much effort onto that.
And even simpler stuff like Joule ringers and earth batteries that to run them to power low power systems. You can power that lots of low power systems with an earth battery, and supply plenty of light with a Joule ringer that's well built, that will put out plenty of light for hours with barely any charge at all, because it's just sitting there and ringing the charge. It's oscillating that charge inside of itself for pretty efficiently. So there's lots of fun stuff to play with. That's like right on the fringe. You can go on YouTube and find the frickin' plans right there. I've built like a bunch of stuff off of YouTube videos that have produced some fun effects, like the aforementioned Joule ringers. Those things are easy to build. You can wind your own transformer in a couple of hours, and it's so rewarding to play with something like that, because you learn a lot just from how it fits together. There's a feel for how it all works too. Beyond
nothing is a better teacher than experience.
Yeah, totally.
It is tremendously gratifying to construct something with your own hands that's the culmination of your current knowledge and see it work. Oh my god!
I'm such an engineer. I'm like, yeah, it's
Yeah, this is what we get off on. This is,
Yeah.
people that don't build or create just will not quite
Yeah.
grasp the satisfaction that comes from a successful challenge.
Totally. I build IoT devices right now. That's my thing. I'm a software engineer by day, but I play around with hardware IoT devices by night. So I'm playing around with different concepts with network devices that are interchanging data to do various mostly artistic things right now. But it's so much fun to play with. Like you can come up with a couple of simple concepts, and once you've played around with it a few times, you can model something very fast and see some really interesting things. At least to have a lot of fun. And tell you what, when you're in quarantine and there's nothing else going on, it's good to have a hobby. That's for sure.
Yeah, I don't understand how there are so many people out there that are they're trying to find something to entertain themselves, and they're absolutely lost without the public interaction. I'm like, did you guys have a personality before all this happened? I mean, did you ever spend any time, I don't know, learning something, becoming somebody?
Yeah, I don't remember the time I was. So yeah.
Yeah, they're traumatized in the absence of those validations continuously flowing in.
Yeah.
Well, how can I be a good sheep if I'm not surrounded by other sheep? I don't know where my herd is, where my flock is. Yeah, we were all on varying degrees of that. I finally found my flock. It's obviously here with fellow researchers and engineers and physicists. So that's finally my little group. But I'm just following what I know too, in some manner of speaking. It's just not the narrative that I've been taught.
Just let me know before you sell your technology to the drone company, because I need to start working on that drone shielding technology, man. Because
don't worry, I'll tell you exactly where the weaknesses are so that you can equip yourself against them. I figured if there's this technology is going to come out anyways, and it's eventually going to be here, somebody's going to do it.
Absolutely. So
I at least want to be the guy that's causing that to happen, so that I know how to eliminate it if it's a problem for me.
So, in terms of how you protect yourself from a drone, what are the different ways that you can think of that to keep a drone army at bay? Like in terms of, I think of maybe electromagnetic means, like somehow jamming them, or physical means, having a net. But other than that, it's difficult.
All I would tell you is this: if you ever find a drone that can fly directly in front of an old Soviet radar transmitter and stay in the air after its first pulse, then you'll have me thoroughly scared. But the impulse waveform in volts per meter coming out of those radar transmitters is so intense, it's so extreme, that electronics fully shielded inside of Faraday cases stand absolutely no chance at protecting against it.
What distance are you talking about, though?
It's fairly close range, but you can Yagi these things and make them highly directional. So if you can target and see a drone and hit it with a laser, then you can take it out of the air using the same type of tech.
Right, that's true.
I mean, they're already just basic disruption technologies. Drone disruption tech, like a microwave transmitter on the general bands that the RC or satellite controls work on. That all it does is drown out the receiving ability of the thing to communicate, and so then it just goes into default and does what it's supposed to do when it loses signal. Generally, that's land. But you could, of course, knowing that this would be a problem, program the drones not to land. Just program the drones to instead, say, randomly increase altitude, or fly off in one direction as fast as they can to try to get away from the signal interference. That's something else that they would get away from you, but they would be just fine. But if you hit them with a radar pulse, they're not going to be just fine. It's not just a disruption, it's a destruction of the internal electronics. And so that's one way that works universally with any electronics.
Yeah, that's true. That's true.
I'm going to end the stream right here.
Sounds good.
Almost 4 hours going. All right, man.
Wow.
Oh my God.
I did not know that.
We can keep going. We can keep this discussion going, so don't hang up the Skype call. So, later, guys.
Well, thanks for having us on again, man. It's been an interesting show and a unique crowd this time.
Yeah, it's always fun, man. We're going to get more and more different people on as we go. More discussions going, and more different ideas and debates. It's fun. So thanks for watching, and tune next time at the Dig Deeper.